Test 1, 2. Okay, that one worked. Check 1, 2.
Great to see you all here. From far away places. There's seats up front. I won't get good in the front. Also, not here to the side. The focus being left for those of you who are wondering where you're at. Seats up front, seat over here on the side. Middle.
Is the micro? Oh, good. The microphone's on. You can hear me. All right. Couple more people getting their seats. You're in focus meeting 11. Hopefully that's the right place. All right. It's good to see all your faces. A couple more people coming in. All right. There's some seats here, some up front. Yeah, coming late, you have to sit up front. Oh. All right. I'm Chris Jacobs from the Jet Propulsion Laboratory in Pasadena, California. I'm the meeting organizer My co-chair's in the front row. She'll be our first speaker. We'll introduce her there. But right now we have the privilege of having Takalani Nimanangi from the Department of Science and Innovation. And he's the Director of Astronomy for the whole country. So it's quite an honor to have him. He's going to come and give us a word of welcome. Takalani, come on up.
Hey, good morning and welcome everyone. It's a great pleasure to be here, and actually for us as the government, the Department of Science and Innovation, to be hosting you here in South Africa at this very important gathering, and also a very historic meeting for us. Astrometry, plays, a very key role, in the world of, astronomy. So let me just give you a sense that within the South African, astronomy, we currently busy developing our next roadmap for the multi-wavelength astronomy, which is coming to an end in 2025. It was kind of a 10-year roadmap. We started in 2015. So we're busy consulting with our astronomy community. And one of the key pillars of the new strategy is on fundamental astronomy, space geodesy, and astrometry. Because I think our community recognizes the importance of astrometry, as a field that is really involved with making sure that we have very precise, measurements, for celestial frames, but also for many other, applications, in astronomy and beyond. Our facilities in RTBS Hoek, participate as part of the global network of celestial reference frameworks, as well as VLBI and geodesy. As some of you will know, that we have a 26-meter dish in RTBS Hoek, as well as a 15-meter dish, and a range of other instruments, that, help us to participate in this, in this field. When our minister came to do the opening ceremony of this event last week, Tuesday, the following day, he was having a series of interviews on national television and other radio platforms. And then I got a call from his office saying that we want to know what are some of the day-to-day benefits of what you guys are doing here with astronomy. And of course, we had to, in a few minutes, develop a document for that. And one of those was around astrometry, because we could, say to the minister that, as part of the work that you are doing, astrometry and other related disciplines contribute to accuracy of time measurements, as well as GPS systems, which have got day-to-day applications, such as in navigation, in telecommunications, and many other applications that are so relevant. So I think the work that you are doing is very important, obviously, in advancing astronomy. And even today, when there is a search for exoplanets, so once again, astrometry is playing a very, a key role. And it's amazing that I think the this field has grown so much from the early days where it was just about maybe creating catalogs, for the stars, to, many various modern applications. So I think we look forward to these interesting topics that you are going to be discussing here from a multi-wavelength, perspective. And it will, and also to network with each other. I think this is very valuable in continuing to develop, techniques and better ways of doing this. So I think with those few words, I'd like to wish you all a very productive meeting in the next 2 days. So thank you very much.
Thank you very much for the talk. My name is Fisifanse. I'm going to be the chair for today's morning session. And our first contributed talk is going to be from Alet David on astrometry in Africa.
Oops, I just have to. There we go. Morning, everyone. I'm now kind of Takalani, not sure what I'm going to say anymore. I think you covered everything. So thank you for that. Let us move. So, is that my talk or? Whoopsie. Sorry, I'm just figuring out the tech here. No, how am I going back? Okay, that's actually the first slide. I thought it was the IAU main slide that shows on the background there. So yes, my name's Alet David. I'm at the Department of Science and Innovation with Takalani there. And yes, I'll be talking about astrometry in Africa. So welcome again to the IAU. I think Takalani has just said, but also during the opening talks this week and many other of the sessions, that this is the first time this GA is in Africa. This is a very significant event. And also welcome to our FM11 session. And because this session has a lot of focus on Africa, and we did a lot of advertising, on also attracting talks from Africa. I can go to the next slide. We got a very special feature in the African Science Stars magazine for our FM11 session. And I actually have it here with me. So please go down, get yourselves a copy, African Science Stars magazine, and I'll send it around. And apologies for my voice. I think everybody is a little sick at the weather and everything here in Cape Town. Sorry for the weather. I heard it's improving, I think from Friday when the event is done. But yeah, I hope this voice will not fail me before the end of this talk. I can actually just look there. That's much better. So during the opening talks, there were also, the IAU president, our own minister, Bladen Zamande from the Department of Science and Innovation, also mentioned, how African civilizations have a rich history of astronomy dating back to ancient times. And this is, of course, because celestial observations were crucial. It still is, but it were crucial back then as well for navigation, timekeeping, calendar development, but also, of course, it held profound cultural and spiritual significance for ancient civilizations. But then many aspects of, what we refer to as the ancient history of astronomy is really actually the ancient history of astrometry, I believe, because celestial observations, like I said, were crucial for navigation, timekeeping, astrometry, you see. It's actually astrometry because this formed a fundamental part of early astronomical practices. So really what we're talking about is astrometry. And many examples were given, I think Egypt, Mali, some of the more well-known examples. I just chose one today, highlighting the ancient history of astrometry. And one that I found very interesting, and that is Ethiopia and the ancient history of Ethiopia. Things like this large structures they called an obelisk in Ethiopia. There are many smaller ones as well in Ethiopia. They believed to be about 1,600 years old at least, and that they may have been aligned with celestial bodies. But what I find most interesting is the Ethiopian calendar, and I don't know if you know about this, but Ethiopia still till today uses their ancient calendar, which has its roots in ancient Egyptian calendar, and they have 13 months, not 12. So 13 months with 30 days, and then a 13th month with, I think, 4 or 5 days. And in general, their year is about 7 to 8 years behind the Gregorian calendar. So they are now in 2616. So just an interesting example of the ancient history in Africa and astrometry. But modern astrometry in South Africa, or astronomy for that matter, really has its root in sea navigation challenges that was faced by European settlers along the coast of Cape Town in the 17th and 18th century, and then the need for accurate navigation, and of course with that, the need for precise stellar positions for this accurate navigation. Now, one of the most notable figures in modern history of astronomy in South Africa is this French astronomer, called Nicolas de la Caille. And he spent 2 years where he catalogued almost 10,000 stars in the Cape of Good Hope. And this was specifically to aid navigation at that time. And then some years later, this led also to the establishment of the Royal Observatory in the Cape of Good Hope. They continued this work of cataloging the stars, and one of the biggest reason for establishing this Royal Observatory of the Cape of Good Hope was astrometry, and specifically for navigation. This eventually led to, and I mean, this was a settler's hut, and back in 1820, and this eventually led to the establishment of what is now called the South African Astronomical Observatory, which maybe some of you have visited during your time here in Cape Town. It's the main facility in South Africa for astronomy, optical and infrared astronomy, but that's the history, and all linked to astrometry and the need for accurate navigation. So very interesting stuff. This was also the first permanent observatory, this Royal Observatory of the Cape of Good Hope, on the African continent, and the first of its kind in the Southern Hemisphere. So really, this was the start of modern history in Africa as such. Okay. There we go. And then we go over to radio astronomy, and Takalani also already mentioned the Hartbeespoort Radio Astronomy Observatory. This observatory was constructed in 1961. There's a nice picture during construction in 1961. It was then known as the Deep Space Facility 51. It was constructed by NASA, this big 26-meter telescope, and it was part of the Deep Space Network at the time that helped with the unmanned and also manned missions to the Mars and some of the other planets. So in 1974, can I move this thing a bit? That's much better. I feel like I'm doing this all the time. So in 1974, this became the Hartbeespoort Radio Astronomy Observatory, and since then, it has been a very crucial component in VLBI networks, not just for astrometry, but also for geodesy, for astronomy. It takes part in many VLBI observations, and really it's its geographic location here in the Southern Hemisphere that makes it very crucial. It gives us the long north-south baselines to Europe, east-west to Australia, and it actually started geodetic VLBI observations, geodetic and astrometric VLBI observations in the early 1980s already. This telescope is still standing, it's still doing wonderful work, and still contributing to astrometry significantly through VLBI. All right, now looking ahead, there's many things happening. We are very excited about the future of astrometry, specifically with things happening in South Africa and across Africa. This is just giving you kind of a look of the landscape in South Africa at the moment. Again, Takalani mentioned some of those. We have two major facilities in South Africa for astronomy, the South African Radio Astronomy Observatory. Of course, they manage all radio astronomy initiatives in the country, but also they coordinate the Africa Radio Astronomy Program. And then the South African Astronomical Observatory, which I talked about before, that's responsible for optical and infrared astronomy in South Africa. But first, let's have a look. Wrong button again. Well, let's have a look at the radio and first Hartbeespoort. So we actually have 3 radio telescopes at the Hartbeespoort facility. That's up north. Don't know, I think some of you have been there before. We still keep on pushing the wrong button. Apologies for that. It's this one. I'm going to keep my finger here and not move it again. Okay, so we still have the 26-meter telescope. That's what it looks like today, or at least this photo is maybe a couple of years old. It's mainly used for astronomy, VLBI, and then for astrometry for reference frame work. There's also a 15-meter telescope, mainly used for geodetic VLBI, and it will be replaced by this new bright and shiny VLBI Global Observing Telescope. Disappeared telescope, and this will be operational sometime towards the end of this year. So many facilities there. We're also hoping for some upgrades on the 26-meter telescope there to maybe go to higher frequencies, maybe a replacement. Now I'm looking at Takalani for that dish. As you know, with Celestial Reference Framework, we've been going up to higher frequencies like 24 gigahertz. We're hoping to go to even higher frequencies. And this is really at the moment, the limit of this big dish is 22 or 24 gigahertz. So some upgrades to this, but yeah, also some new things coming. So very exciting. Okay, there. I talked about the celestial reference frames. South Africa has played or made a huge contribution to the International Celestial Reference Frame. It's one of only a few radio telescopes that does VLBI in the Southern Hemisphere. I showed you the map before. It's also the only radio telescope that participates in regular VLBI observations in the whole of Africa. And it has really been a crucial component in celestial reference framework, both at the historical bands, 2.3, 8.4 gigahertz bands. I'm just showing an example of the source distribution. This was for ICRF3. This is what it currently looks like. We're now working towards ICRF4. I don't want to say too much about it because there will be many talks after mine on the celestial reference frame. But Hartbeespoort has made many contributions to the celestial reference frame, and particularly at K-band. Now, K-band, the 24 gigahertz frame, is an international collaboration, but it's managed from or through South Africa, the K-band celestial reference frame. So another, important aspect of astrometry that comes from Africa. That is again just to show a map. This is for the International Celestial Reference Frame at K-band. This is the network that we're currently using with stations with K-band receivers in the world. The EVN recently joined observations, which we're very excited about. But as you can see, nothing on the African continent and nothing for many kilometers in either way. So a very crucial component, this facility in astrometry and specifically the International Celestial Reference Frame. Of course, Hartbeespoort, and I need to mention this, is also one of a few core geodetic sites in the world. That means it doesn't only have the VLBI telescopes, but all the main geodetic instruments on one facility. And again, it's only one of only 2 in the Southern Hemisphere and one of only a few in the world. So again, making it a very crucial a station in geodesy as well. And of course, astrometry, the reference frame, contribute to these measurements. Okay, going back to our slide here on South Africa. Next, I'll talk a bit about the SKA. Of course, the SKA itself will also have in its VLBI mode on long baselines above 5 gigahertz, a very important role to play in future, we believe, in astrometry, to measure more weaker sources for the celestial reference frame. And then talking about Africa, so I already mentioned the Africa Radio Astronomy Program that's being managed by the South African Radio Astronomy Observatory, and this is really for the development in the partner countries, the SKA partner countries, towards the full realization of the SKA. So a lot of work has happened in Africa through this program, but things that are also exciting for our work that we look forward to. So there is the Ghana 32-meter radio telescope. This was a conversion from an old telecommunications dish. This telescope is now operational. We hope that it will join VLBI observations soon, and there's many opportunities there, having now finally a second radio telescope on the African continent that can do VLBI. And now I'm going to do this again for those who haven't seen it. They, as part of the I think it's a Dara stand. They have some flyers there. If you're interested, go and talk to the people. The Ghana Radio Telescope. I'll send this around as well. Oh, I actually need some water, but I think I'll make it. And the other one I wanted to mention is the African Millimeter Telescope. I tried to get a flyer from them this morning as well, but the stand was gone. There was a nice big stand, I think, on the African Millimeter Telescope as well. This will be the first millimeter wave band telescope on the African continent. Of course, it will be linked to the Event Horizon Telescope, but there are definite plans to also put centimeter wavelength receivers on this telescope, like 24 gigahertz and higher, and this will really be significant in, also helping the celestial reference frame observations in future. So we're really looking forward to that. And tomorrow, during this session on FM11 astrometry, there will be a talk on the African Millimeter Telescope. So yes, please stick around. I don't have the flyer, but there will be a talk on it. And similarly, there's also a similar project to build such a millimeter telescope on Mount Kilimanjaro in Tanzania. There will also be a talk on that tomorrow. So please, join us again tomorrow for that as well. And then also Botswana will get its first radio telescope pretty soon. We're very excited about that. That will be the third one. Again, that will be important for our astrometry work as well, but for VLBI in general. So lots of exciting things happening on the African continent. Now I have to do this. Apologies. All right, yes, and of course, as part of the Africa Radio Astronomy Program, there's also been a lot of training going on in Africa. One of those initiatives is the Development in Africa with Radio Astronomy, where we train students in the SKA partner countries in Africa. This is a photo I cannot even remember from many years ago. This has been happening since 2015. It's ongoing. There's some new funding. So we're in phase 3 of this project this year. But the important thing I wanted to highlight, it's not just radio or astronomy training. We've trained many students also in astrometry and geodesy. And maybe you've seen many of these students that came through this project had talks at this GA, and some of them in this FM11 session today or tomorrow. So some of them are in the group here joining us here and giving some presentations. So this has been a very successful program in Africa. Some more things. I think now I had to go over to the South African Astronomical Observatory. That was just to mention we also have fantastic optical facilities like the SALT 10-meter telescope in Sutherland, which is the largest single optical telescope in the Southern Hemisphere. And of course, this also presents opportunities to enhance the ICRF, for example, through measuring redshifts of our ICRF sources, for sources that may be strong in radio, but faint in the optical. So yes, also the optical facilities that can play a role in the work that we are doing here. And then finally, I'm going to do some advertising. So this is my last slide, because I'm kind of an astronomer, geodesist, and now in government, so a mix of all. So I have to do some advertising as well on the geodesy side. But of course, our astrometry reference frames play a big role in what we call, go back a little, the Global Geodetic Reference Frame. So this is a resolution from the United Nations on establishing this Global Geodetic Reference Frame. And now at the end of September, we have a whole Geodesy Day to talk about the implementation of this resolution for a global geodetic reference frame. This is at the UN Science Summit in New York, and we're hoping to maybe see many of you there in person or online listening to our day-long session. It's specifically focused on Africa and enhancing, geodesy, which includes astrometry, across Africa, specifically in terms of instrumentation. So that's my final slide. Thank you so much, and enjoy the rest of your focus meeting. I had one on the training as well in Africa. I'll also send this around. Sorry, thank you so much. Oh yeah, so I guess questions.
Yeah, thank you so much, Alette, for the talk. Are there any questions? Are there any questions online? All right.
Are people online, they can't hear us.
Yeah. All right. Okay, let's thank our speaker.
Thanks a lot.
All right, so our next invited talk is Patrick Charlot, and he'll be talking about towards the next multi-waveband realization of the International Celestial Reference Frame.
Okay. So I'm going to give you an update on the ICRF and the future plan for ICRF. Should I do something? Is it better? Should be okay. So as I said, I'm going to talk about International Celestial Reference Frame and the future plan. Oops. Okay, so this will be the outline of this talk. First, I will give you a brief history on the ICRF. I will talk about the improvements since the latest ICRF version was made, ICRF 3. I will then talk about the plans that we have for multi-waveband ICRF, mention the issues that we have to deal with, and then present the timeline. So in one slide, a brief history of ICRF. So the first ICRF was done 25 years ago. It has 600 sources. The second one, ICRF 2, was done in 2009. It has 3,400 sources. And the latest one, ICRF 3, was done 6 years ago, and it has 4,600 sources. And all these frames have been adopted by the IAU, each new version replacing the previous one. Talking specifically about ICF3, ICF3 has three components: the traditional S6 band component, which was dates back to 25 years ago more than 45 years ago for the first observations. But since ICF3, there are also two new components: a K-band component, 24 gigahertz, which has 800 sources, and an XKA band component, 32 gigahertz, which has about 700 sources. But at the same time, VLBI was the only technique to be able to produce a reference frame with high accuracy, was not alone anymore because the space mission Gaia came on and produced the first optical realization of the extragalactic frame in 2018 with a frame that is called Gaia CRF2 and which has 500,000 objects. With another versions 2 years later, Gaia CRF3, which have three times more objects. And this last frame, Gaia CRF3, has been adopted by the IAU at the previous General Assembly as the optical realization of the extragalactic frame. So first, I would like so this was a brief history of optical and radio in terms of ICRF. I want now to give you an update because ICRF3 was made 6 years ago. Since that time, new observations have been acquired. So I would just give you a brief one slide per frequency to give you an update. And there will be other talks after me. We will give some details. So talking about ICRF3 in S6 band, there are now, as Alex said, there are now 5,700 observations. This is 25% more, 25% more sources than ICRF3. And in terms of observations, it's 40% more observations. And as I said, the data span is 45 years now. The precision is indicated on the right. There is an improvement of about 20% compared to ICRF3. K-band, 24 gigahertz. So it's the improvement at the time of ICRF3, which this was really the beginning of K-band. So the frame could be strengthened a lot since that time. There are 60% more sources. The number of observations has been multiplied by a factor of 5. And there is also quite an improvement on the precision side. XKA band, the number of sources has not changed much, but the number of observations has doubled, which means that the precisions also improve by some amount compared to ICRF3. But there are also two new potential frames that were not in ICRF3, but maybe they could be considered in the future. The first is Q-band, 43 gigahertz, and the first frame was produced recently with it's based on 3 sessions acquired with the data acquired with a very long baseline array, 400 sources and 70,000 observations. The precision is not yet there, but it's 200 microarc second and 3 in right assumption and 300 microarc second declination. But it shows that there is a potential. But of course, there is nothing in the source because the only observations that were possible were made with the VLBA. And in respects to what Alex said before, I think it was really great if Artemis 2 could be upgraded to Q-band, and there could be a nice sensitive baseline to Argentina with the CAR telescope that is being built there. So this would be really great. So the other thing is the VGOS. So VGOS is the new VLBI global observing system being built by the IVS. And a first frame was also produced recently with this new system. So VGOS observe in 4 frequency bands, 3, 5, 6, 10 gigahertz. This may evolve in the future, but this is what this is for now. So there are 400 sources, 1.4 million observations, and the precision is quite good, down to 30, 40 microclock second. So the potential is there, but again, there is nothing in the source because there is no thousand or not many thousand stations at the moment. This is going to change in the next few years, especially with the VGOS telescope in Hartbeespoort that is going to start soon, as Alex said, and also antennas in the south. So this is going to evolve in the next few years. So if I summarize now the situation in general with respect to the ICRF, we have 3 frames in the radio, X, K, and K band, 1 in the optical with Gaia, all with roughly the same level of precision, and potentially 2 more frames that will come up in the future in radio at Cubion and with VGOS. Gaia has 300 more sources, but on the other hand, VLBI is mandatory for geodesy, Earth rotation, spacecraft navigations, and many things. So each frame has its own value, and cooperation between all these groups might prevail over competition. So the next stage is to build a multi-wave band frame. And to this end, a working group of the IAU was formed 3 years ago to study and ultimately to build this multi-wave band frame. So it has 18 members from 14 institutions in 10 different countries with a wide range of expertise. So what are the objectives of the working group? So the objectives are to work towards the realization of a multi-wave band celestial reference frame, incorporating position in radio and optical band, while ensuring maximum consistency between all these bands. So in detail, the goal is to produce the next generation frame at SXK and XK band, or other radio band that may emerge, like Cubion and VGOS, to match this with the optical realization by Gaia, and to place all such positions on a common grid in order to guarantee consistency of the positions over time. But it's not so easy. There are a number of issues, like inhomogeneity of the sky distribution, with galactocentric acceleration, alignment of individual frame. I will just say a few words about this. Just one point on the inhomogeneity of the sky distribution. ICRF has shown a significant north-south asymmetry. By this, I mean that there are less sources in the deep source, minus 45 degrees. As I said before, this is because there are not enough VLBI antenna in the south. Unfortunately, things may evolve sourcely, but this is a situation that we will have to live with for some time in the future, even if I'm sure it will evolve. What I didn't say is that the southern sources have also much lower precision, and there is this asymmetry in the frame. Gaia is much more uniform, but it has only a few sources, less sources along the galactic plane due to galactic extensions, and this is not going to improve with the future releases. But on the other hand, VLBI may help to identify quasars among Gaia data in this region, because for the ICS sources that are known, they could be pinpointed and found within the Gaia. So this is one thing that we have to deal with. Another thing is the galactocentric acceleration. This is the acceleration of the motion of the solar system around the galactic center. For the first time, this effect manifests itself through the apparent motion of the extragalactic sources, which normally should not move. It was first derived from ICRF3 and Gaia CRF3, but there is a difference of 1.8 sigma between the two determinations. I should also mention that the approach was not the same for VLBI in Gaia. In VLBI, the amplitude of the vector was estimated and implemented in the modeling for ICRF3, whereas in the case of Gaia, the proper motion of the sources were considered as part of the catalog and the effect was not corrected. So in the perspective of a multi-waveband frame, we need to find and adopt a common approach to make the acceleration vector and the epoch of the frame consistent in all the bands. So new value for Gaia are expected for that from data release 4, which should be by mid-2026, and the final one with the final Gaia data release beyond 2030. And VLBI value can be adopted on the same time scale. Another thing is the alignment of frames. Whether we should use all common sources to align the frame or only a subset of them is a matter of debate. Also, a difficulty is that the sources do not have the same position, exactly the same position as all the frequencies because of physical effects in the sources. And also these positions may vary with time, as revealed by VLBI, because of the evolution of the internal structure. So this is somewhat a tricky business, but the working group decided to have a pragmatic approach and to try to identify a subset of sources, ideally, which would have stable position and no measurable offset between bands. So this is the goal that we should try to attain to build this frame. Well, I will perhaps not spend too much time on this, but with this new frame, different frequencies, we need to have to adopt a proper terminology to make sure that we always talk about the same thing when we talk about different frequency. So first we decided that ICRF would be valid for every frame. This was initially, ICRF was defined without a waveband in mind, but in practice, since it was connected to the VLBI frame, people thought this was the VLBI, but in fact, it is general. So we came up with this terminology. So every individual frame would be referred to ICRF NW-F, where N is the ICRF numbering, ICRF 1, 2, 3, 4, 5. W is a code to identify the waveband, radio or optical with Gaia, so R and G. And then you can have another identifier to specify the specific frequency, X-band, K-band, K-band, and possibly others. So the timeline of the work. So the work during the first triennium, of the working group during the past 3 years was dedicated to study the issues like those that are mentioned, to identify and study the issues that are coming up with when you want to build such a frame. As I said, data release for Gaia will be published by mid-26, while Gaia DR5 will be published beyond the final release of Gaia will be published beyond 2030. As I said, the volume of data on the VLBI side has considerably increased since ICRF. So this justifies having a new ICRF without waiting for the final Gaia data release that will be beyond 2030. We should also keep in mind the future IAU General Assembly for administrative purposes, because we need to have the future ICRF to be adopted by the IAU. So it could be 2027, 2030, 2033. And based on all this, we agreed that the next ICRF should be done by 2027. That would be ICRF 4. It will include Gaia DR4, while the ICRF 5 would be after the final Gaia release. So the work during the next 3 years from this working group will be dedicated to building ICRF 3. And that's it. Thank you very much.
Thank you so much, Patrick. Do we have any questions?
Hi, thanks for the summary. Really nice summary. Two questions. One fairly simple. I've heard a lot about Q-band in the past, but I've always had the impression that the number of observations that can be obtained is relatively limited because of weather, which limits its utility. Do you see that changing?
Well, the weather is not going to change, I think. So it's still going to same. But the thing when the initial Q-band observation was done some
20 years ago,
2005 around that time, I mean the sensitivity of the telescope was not the one that we have now. So we should be able to see more sources. On the other hand, the troposphere is not going to, I mean, the variability of the troposphere is not going to change. So you need to integrate on short time scale. But as I said, this is a work in progress. 3 sessions were carried out with the VLBA. I mean, because of the higher resolution at Q-band, there is in principle, a higher potential for astrometry. We have to see in the end if this works, if the sources are still point-like enough at this even higher resolution. So there are a number of things that needs to be investigated, and that will be investigated, and then we could have a final, decision on this.
And the second, I don't know if it's a question or a comment, but has the working group given any thought or much thought to identifying science drivers that would push for a much improved precision?
You mean science drivers?
Yeah.
Well, the science drivers are the same as they have always been.
Enumerating those perhaps more specifically. Enumerating those perhaps more specifically. Listing them, describing them more specifically. Yeah.
Example, well, everything, this ICRF is the basic for positioning everything in the sky as a whole. It's served for geodesy and many things. Well, I can't list them, but there are differential astrometry, spacecraft navigation, and everything. You cannot reach a millimeter in geodesy if you don't have a celestial frame that has the same level of accuracy in the sky. People claim about millimeter, but you actually need a reference frame that has the same accuracy in the sky, and all what's behind geodesy, millimeter geodesy, sea level rise, many geophysical effects that show up at these levels. And you are not going to do that if you don't have the necessary accuracy in the sky and a proper frame that has the same accuracy.
Yeah, just to add to your comment, a millimeter is about 20 microarc seconds on the longest baselines. And the differential people, I think Maria and Richard have differential VLBI talks. They're getting 10 microarc seconds and pushing further on down with that. The spacecraft people, the CCSDS, are asking for 100 microarc seconds by the end of the decade, and they have a desirement for doing a factor 2 better down to 50 microarc seconds, and we have systematics above that level. So those are a few examples. Also note on the Q-band, Hanna Krasna has a poster down in the poster session. So
yes, So I should have mentioned that, but I forgot. There's a poster. I mentioned the talk by David Gordon and Chris, but there are two posters, one about Q-band and one about VGOS, that during this FM11 meeting.
Hi, Patrick. Thank you. Very nice talk. This is a very basic question. So with this multi-wavelength catalog, what will be the main benefit? Because I can see that they can be the sources, they can intrinsically be very different. So you will have to select a small number of them.
It's a benefit.
So what is the aim? To increase the precision for a smaller number of sources?
The benefit is to, for a given source, you will pick up the position that will be consistent as far as we can, that will be fully consistent within all the catalog. If you pick up your favorite source, then you will get the positions in all the frequencies, including optical, fully consistent.
Mm-hmm. But will be in a smaller subset.
Well,
because naturally, intrinsically, they can be different, no? The
yes,
positions,
but
they are different.
They will be different. This will be a different position. It's not going to be a combined catalog. It's going to be different position for each frequency.
Okay.
So if you pick up one source, you will have a position at S6, at K,
Okay.
XK, in the optical, and you will be able to take it with assuming that it's all on the same celestial frame in the sky,
Okay.
in a fully consistent frame.
One more question and then we'll.
Thank you very much for the talk. My question is about, is it possible for the working group to consider the motion of the sources in the future? Because the galactocentric acceleration is actually apparent motion of the extragalactic sources. And then the Gaia DR4 and 5, I think the accuracy for the source motion will be much better than current database. So my question is about the proper motion. Is there any project or possible?
Well, this is a matter of discussion for the working group, especially in terms of the galactic array acceleration, how we proceed with this. Yeah, but the extragalactic sources are on the long-term base are not supposed to move on the sky. They are supposed to be stable, and if they have motions, it comes from their internal evolution, internal evolution and internal structure.
Okay, thank you.
Thank you, Patrick. Thank you so much, Patrick. Okay, so
To talk at FM11 is something from South Africa, from the LOC.
thank you for that. All right, so our next contributor talk is from David Gordon, and he'll be talking to us about progress towards ICRF4 at XS and K bands. Sorry, so this is front, back, pointer. The timer.
This is forward.
Forward, backwards,
Yeah.
and this is the pointer.
Okay.
For yeah. Okay, they're going to bring up your
All right.
talk, and then your timer is at the bottom there. So when you've got 2 minutes, the orange light will go on.
All right. This will be 14. Okay. I'm going to talk about specifically about the status of XS and K band, and Patrick and Alette have actually shown a lot of my slides already, but we'll go ahead. Since ICRF3, it's been 6 years, and work towards expanding, maintaining, and monitoring the ICRF has continued at all 3 of the radio bands. In particular, at X band, there's been quite a bit of work at the U.S. Naval Observatory, where we do monthly XS PLBA sessions, astrometry sessions. And And we do the K-band analysis that Alette DeWitt uh, schedules. These are K-band sessions once a month also. And the IVS sessions have contributed somewhat to astrometry as well. Well, I'm going to skip this. You've already gone over ICRF working group. So for starting with the excess catalog, the current situation, as I was saying, we do a lot of work at USNO, also IVS sessions. The AOV and AUA sessions have added about 120 sources. The VLBA sessions have added about 1,100 sources, and we now have 5,770 sources with very good precision. The amount of data has increased at SX by 42%, number of sources by 27%, the overall precision by 15%. But if you look at just the common sources between ICR3 and the current latest solution, precision has improved by 26%. We're approaching better than 100 microarc seconds in right ascension, and declination still needs some work. These are inflated errors, inflated as they were in ICRF3. Moving on, so there's a plot on the left of not sure how this works. Of ICRF3 sources, 4,536. We had to drop one source because it shows a much different position, 3C48, but there are now 5,770 sources. You can see that we concentrated somewhat along the ecliptic, and this shows the difference. So we had about 500 sources along the ecliptic to give the navigation people more sources to choose from. And there are about 500 additional sources. The number of sources added in the south, unfortunately, is not so great. And that's unfortunately not going to be able to change much in the next 3 years. And I want to go over the role that the VLBA produced in improving the ICRF. The VLBA has observed 96% of the excess sources, so there are only 4% that have been observed only in IVS sessions. And importantly, 68% of the excess sources have been observed only on the VLBA. And this includes any sessions that have VLBA. So you can see if there were no VLBA, this is what the ICRF would be at excess. It'd be much smaller. So we do owe a lot. And most of the observing in the past 6 years has been done on the VLBA under time that's paid for by the U.S. Naval Observatory. Over the next 3 years, we're going to continue observing on the VLBA monthly. And there's going to be an effort to monitor a set of sources that show very small offsets from Gaia, less than 1 sigma. Patrick didn't mention this, but there's 785 sources that he and colleagues have identified that show less than 1 sigma offset. These could be used as, we're going to try to get images and positions twice a year of these. And they're potentially very good sources for alignment between the radio and the Gaia catalogs. Many of them, however, are too weak to be defining sources. We're going to concentrate on improving the precision of the weakest sources, few sources that have been only observed 1 time or less than 4. I have a list of blazar candidates that we're trying to look at. Blazars are potentially the most stable sources. Blazar is where the jet is pointing in our direction. So motion variations in the emission along the jet would not show up as any change in position. And there's going to be an effort to improve the CRDS sessions, IVS sessions in the deep south, but we're not sure how far that's going to get. Moving on to K-band, we've done monthly K-band sessions on the VLBA. We've added 475 sources since ICRF3. And we have now, and for ICRF3, we only had two networks. We had the VLBA and we had the Hartway-O to Hobart baseline. But since then, we had a 7-station Southern Hemisphere session, which included Parks and Hobart and Hartway-O. And we've had additional Hartway-O to Hobart sessions, but unfortunately, Hobart hasn't been able to participate for several years. And we've had observations between Yebbies and Hartway-O that have added a long north-south baseline, which are improving the declination precision. And we've had these networks with the Korean VLBI networks, which includes Hartway-O, sometimes Sejong, Yebbies, Mopra, and I think one with Hobart also. So the catalog has increased by 60% more sources, for 28% better precision. But if you look at the same sources for 824, the precision is 40% better. So this shows ICRF3 K-band, and this is the current catalog. I don't expect the number of sources at this point to increase by much. It depends on Alette actually scheduling the sessions, but it shows the difference. There's been no effort to densify the ecliptic or the galactic plane, but that's something we could consider. And issues at K-band briefly mentioned that 99% of the data comes from the VLBA, and that's good and bad, of course. We get great data from the VLBA. The other sessions should increase over the next 3 years, but probably the percentage won't increase since we continue doing VLBA sessions. We have lower declination precision, mainly because the north-south extent of the VLBA is only half as much as its east-west extent. So longer north-south baselines to Hartway-O, Mopra, Hartway-O to Yebbies, that could help. We hope to get more of that data, and lower precision generally for southern sources that are not observed with the VLBA. And we're not getting reobserving many of these sources, unfortunately, because we rarely have two stations in the southern hemisphere in our sessions. The networks are somewhat disjoint, the VLBA versus the others. There's only the other sessions all have Hartway-O, which is good in connecting to the VLBA, and we have a good connection from the VLBA to Hartway-O due to RDV sessions. But there can be some rotations of the networks, which can produce rotations of the celestial reference frame. We are approved for doing 10 global EVN plus VLBA plus KVN sessions over the next 3 years. We hope to get many of those processed and analyzed before ICRF4, and that should stabilize. That should improve this problem with joining the networks together. Okay. What we plan to do in the next 3 years, continue on the VLBA, continue the KVN sessions, and work with these 10 EVN sessions, which could head up at 26 stations. I'll show a plot of that next. Other possibilities, which probably won't have much effect in the next 3 years, unfortunately, are the installation of the 8 to 40 gigahertz receivers on the VLBA antennas. They've been approved, but they're not quite funded yet. And it would probably take a couple of years or more for them to come into existence. But we could do dual KX for ionosphere calibration. Right now we're doing ionosphere calibration from GNSS ionosphere maps, and that leads to some essentially white noise errors. There's a 40 meter in Thailand that could participate perhaps. I don't know exactly what's the status, but it could extend the observing down to minus 60 degrees instead of the minus 45 of the VLBA. And there's this new Chinese Argentina antenna. We're trying to get time on that, but it's to be determined. And lastly, let's see, not lastly, this is the possible stations for the global EVN, KVN, VLBA network. This would be a really wonderful network to do K-band or any band research at. Hopefully the first session will be in October. And I think this is my last slide. Just comparing XS and K-band precisions over the past 6 years. The top row shows the precision that we got with ICRF3 for common sources between the two bands, K-band and SX. We see that this is the right ascension and the declination median scaled formal errors. You see that ICRF3 SX was noticeably better than the K-band. But if we look at the latest K-band solution, which has 1,268 common sources with ICRF3 from 2019, to be fair, K-band shows better precision than ICR3 SX currently. But if we realize that XS has also improved, and there's now, comparing the latest solutions between K-band and SX, they're about on par, very similar. Right ascension looks a little more precise for K-band. Declination, where we have lower north-south coverage and larger noise floor, essentially, the precision is a little bit less. But it's essentially on par with XS. And I believe that's the last slide. I want to, of course, mention that imaging at XS band is being done at USNO. Chris DeLulu there, if you want to hear about it, talk to him. Alette DeWitt is doing K-band imaging at Hard Rayo, or at least used to before she moved. Hopefully that's still going on. And the work that we do at USNO for XS and K-band supports the USNO mission, which is maintain the celestial reference frame and provide Earth orientation. So thank you. Questions?
David, do we have any questions?
Hello, it's more a request. When you finally release the catalogs, would it be possible to also release the respective terrestrial part as well as the EOPs involved?
What was the first?
And the terrestrial reference frame that you use.
Yes, it would be. Yeah.
Any other questions? Do we have any questions online? All right. Can we please thank our speaker? Our next talk needs no introduction. We're gonna have a talk from Chris Jacobs about the XKA at 8.32 gigahertz 2024B celestial reference frame systematic errors.
Thanks. Thank you. Do I need to click it to start it? Okay. This is another frequency in the radio ICRF. I'm going to talk today about trying to reweight the data in a new way to reduce systematics. This is a picture of the coverage. There's about 700 sources. Okay, we're a little bit behind, so I'm going to zip through some of the intro stuff, but we'll post these online if you want to go back. Our work at JPL on reference frames is driven by spacecraft navigation and also Earth orientation to support spacecraft navigation, but of course it's useful to other applications. We've been part of the ICRF since 2019, and the big news for us in the last 10 years is adding ESA and JAXA station. We're getting support from other spacecraft people. Our systematic errors that we're worried about are source structure and troposphere, and comparisons with SX show some issues that I'll cover. S-band is kind of on its way out because of RFI. X-band is our workhorse frequency. Ka was not driven by a desire for an ICRF necessarily, but the spacecraft needed more bandwidth to bring down telemetry and pretty pictures and things like that. We're fortunate that the astrophysics is nice at Ka band, and I'll show some things there. Okay, the current status, we've got about a 20-year history. Here's the residuals. We have about 140,000 observations. As Patrick mentioned, that's about a factor of 2 since ICRF 3. So we've been well supported, and the addition of ESA and JAXA has helped. Our precision is kind of comparable to the ICRF 3 SX. And as you'll see, the real issue is systematics, not precision. We've been very fortunate that we have large 34-meter antennas and 2 gigabit per second data rates. So the formal precision has not been our issue. Here's a look at the 686 sources. You can see about minus 40 is where the northern stations lose their reach, and the far south, we have a little bit lower precision. Here's our network. The 2 purple baselines are the NASA Deep Space Network. That's what we've had for the full 20 years. In 2013, we added the Argentina station and added the yellow baselines. They've been wonderful. They really strengthen the geometry. The purple plus yellow, I tell people, makes like a bicycle frame. And for the same reason a bicycle frame is strong, this is a strong geometry. We wish we could get more time in Argentina. It's about 12% of our total observations. The issue there is that ESA only has 1 antenna at that longitude, and the DSN, we have several, so we can track spacecraft while we're also doing astrometry. For ESA, they have to stop watching their spacecraft for a day, so its scheduling is a little bit tougher. The orange baselines are the JAXA station up in the mountains of Japan, Misasa. Beautiful antenna, 54 meters, performs very well at Ka band. We've mentioned structure a few times. Here's pictures of a source at 4 different frequencies, S-band, X-band, K, and Q, going from 13 centimeters to 0.7 centimeters, about a factor of 20 in resolution. And you can see that sources become more point-like. The Ka band will be between the other 2 slots. We don't have imaging yet. But this is one of the advantages of Ka, is that the sources are more compact. And to give you some data behind that, here's chi-squared by each source in the XKA catalog. About 10% of the sources have chi-squared above 1, but the vast majority are very close to 1 without doing anything special. So source structure just isn't a huge problem other than a few particular sources. We're very fortunate. The real problem with XKA, as with other frequency bands, is troposphere. The turbulent water vapor is the issue. I've represented that here by the clouds. You get lumps. And as you look down towards the horizon, it tends to increase roughly as 1 over sine elevation. If you're interested, there's some nice papers. The Truhaft-Lange paper is kind of the seminal paper on this topic. We did a conference proceeding some years ago, and you can look at that. Okay, the standard process in astrometric VLBI is to take the data and add white noise until chi-squared equals 1 for each session, and that covers up the systematic errors for that day. This talk, I'm going to explore adding an elevation-dependent noise, assuming that our major error is the troposphere, and as you look at lower and lower elevations, the errors scale with the amount of troposphere you're looking through. I'm going to use a term called air mass, which is just 1 over sine elevation. So the zenith wet over sine elevation is the total line of sight wet troposphere. And I'm going to assume that the first and second station tropospheres are independent. My baselines are 7 to 10,000 kilometers long. That's a pretty good assumption. And then we'll tune by each session. So to convince you that there's an issue, here's chi-squared versus the root sum square of the air masses. And you can see there's a very clear trend, almost a perfect line. There's not as much data at real low, but it's a pretty convincing line. So we're not getting full credit for this high elevation data, and this low elevation data is getting too much weight in the solution, and it distorts the solutions slightly. If I add 5% of the line of sight wet troposphere at each site, I can flatten this curve out. It's not perfectly flat, but it's much better than it was before. You don't get that big slope that we had up to about 2. So it does some good here in the global sense. Unfortunately, when I look at the individual sessions after doing that, we're doing pretty well here, but here we upgraded and got higher data rates. And so the one number doesn't quite fit the entire data set. These newer sessions, they range between a chi-squared of 1 and about 0.4. So just saying take 5% of the wet troposphere gets you in the ballpark, but it's not perfect for all stations for all time. So I went and tuned each session the amount of wet troposphere noise, and you still get a pretty flat curve. It's a little bit of a slope. It's not too bad, but now the chi-squareds are very close to 1 for each session. So not perfect. Reality is a little more complicated than one would hope for. So I'm going to compare now the difference between the white noise tuned per session and the tuned troposphere noise per session. Here's the difference between right ascensions in the XKA and a recent solution that David made at SX. You see 2 features. There's this sine of twice the deck, a quadrupole 2-0 term, and then there's a bit of a tilt also. The quadrupole term's about 160 microarc seconds, 0.8 nanoradians. The linear slope's 1.2 microarc seconds per degree. And this is what I'm saying. The systematics are really dominant. The scatter about this feature is tighter. When we do the elevation dependent noise, that slope is now reduced from 1.2 to 1. So it doesn't fix all problems, but it's a 20% reduction. And this is the same data, the same modeling, just different weighting. The quadrupole itself is not improving a lot, unfortunately. Now, here's the declinations. The slope's not quite as large. We get a slope of 0.95 here and a hint of an equatorial bulge, but it's not statistically significant. When we apply the troposphere dependent weighting, the slope goes down by about 10%, and the quadrupole, or the dipole rather, goes down a little bit, but it's not statistically significant. So the next steps, we've just started with JAXA Misasa 54 meter. With that kind of aperture, we're not SNR limited, so troposphere becomes an issue. ESA Malargüe has improved their instrumentation from 300 to 500 megahertz. We got some data a couple of years ago. We increased the data rate to 2 gigabits, and we think we can probably go up to about 2.7. They just installed a cooled receiver in Malargüe that should reduce the zenith temperature from 70 or 80 down to 40 Kelvin. We're going to test that in September. So all this is going to drive down the thermal errors and make us even more dominated by troposphere. The other thing that David mentioned is the VLBA. We've got an 8 to 40 gigahertz broadband that's been tested, but it hasn't been built yet. Joe Lazio is going to give a talk. Joe's in the back there. You want to raise your hand? He's the guy to talk to about this receiver. Potentially, we could do X, K, and KA simultaneously and get direct comparison of the K and KA frames without taking any more observing time. So that's a really promising thing. And then, of course, the dual band for K. For us at KA, this would add 45 baselines, which is just huge. I've been doing, individual baselines, and it would enable us to do imaging directly at Ka band, which we haven't been able to do up to now. And it would break some of these geometric correlations that are giving us the spherical harmonic distortions. So that's really going to help. Also, this broadband receiver has potential to go to 1 gigahertz bandwidth, analog bandwidth in the short term, and up to 4 gigahertz in the long term if we can find a way to move that many bits. That's quite a bit. So between the larger bandwidth and the larger number of bits, we could get, maybe an order of magnitude delay precision in the long run. Okay, the next step, the character of error is undergoing a change, not just for Ka, but for VGOS and Ka band. As we get higher and higher data rates, the thermal errors, the uncorrelated errors are going down. We're going to be dominated more and more by correlated errors, troposphere, and also clocks. We started at 56 megabits, and we're now at 2 gigabits, and we're just seeing more and more bits as the future goes. I mentioned the Kolmogorov spectrum paper and the conference proceeding. You can get some more details from that. And we have code to implement these. That didn't get done in time for this talk. Hopefully next time I'll be able to give you some more details. So in summary, the XKA has been part of the ICRF3 since the beginning of 2019. We have about 700 sources. We've doubled the number of observations to 140,000. The medium precision is comparable to the SX and K, but we're limited by systematics. Part of that's troposphere, and this reweighting helps with that, but we've got more work to do. These slopes, while they're reduced, are still significant. Hopefully we'll get the VLBA in a few years, and that augmented geometry will help us average out some more things. This quadrupole 2.0 didn't get helped too much by the troposphere weighting. I'm starting to think I've got a bug somewhere. It's 0.8 nanoradians. It's not large, but I think I've got some looking to do. Source structure is good, like we expected. It's only an issue for about 10% of the source, and we have broadband coming up.
Thank you so much, Chris. We have time for one question.
Chris, thank you for a wonderful talk. I have a question. When you make a comparison XKA versus SX, did you try to make Ka only solution with applying atmospheric contribution from genus GIM and to see whether you see the same huge right assertion blob or not?
With applying GNSS?
Using Ka only without X.
Oh, no, I have not tried that. Well, there's a couple sessions where X-band failed where I've applied calibrations, but I haven't done it to the whole thing. Ka ionosphere is typically about 50 picoseconds, something like that. It's not huge. Yeah, thanks. All right.
Let's thank our speaker. Thank you, Chris. As Chris mentioned, we're running a bit behind, but this is our last talk from Oleg Titov, who's going to talk to us about new astrometric solution AUS 2024 by Geoscience in Australia.
Thank you. Thank you. Good morning. I believe if you have a look on the formal errors of most observed radio sources into recent ICRF realizations, ICRF2, ICRF3, you'll find that formal errors of most observed radio sources are the same, about 6 microarc second. And fresh solutions done in the same procedure, in spite of adding 5 million observations, would provide you the same value, 6 microarc second. So I decided to change a bit the procedure. So instead of, it's usually in CalcSolve or software like FIFS using piecewise linear function with duration about 60 minutes, because some duration of 20 minutes does not enough. That does not help to improve formal errors. Instead of the standard procedure, I moved to a least squares collocation method. So if you got typical group delay about 30 picosecond to 1 centimeter and one number of derivations per station about 100, we should get station formal error was about 1 millimeter. And actually, the standard procedure does not provide this value. If you have a look, say, on the formal error of telescope position since 2002, the formal error is about 3.5 millimeters. The limiting factors are correlated noise from the troposphere, from troposphere and clock offset. Twice I decided to use least allocation method to estimate troposphere and clock offset for each individual observation first, and then move it to the data file. So effectively, this is an equation how to estimate troposphere clock. So this is a couple equation with standard least squares method. Here we've got collocation technique to estimate troposphere and clock from for each moment, and using the covariance matrix for the stochastic parameters. So this is correlation function for clock phase and for troposphere. And this is an analytical model how to use it. I don't stay too long on that. And finally, if you've got this troposphere and clock offset for each moment, we can compare, say, for to check out quality of troposphere delay for Cont 11 campaign. Black dot shows estimates from water vapor radiometer provided me by Rudiger Haas, and red dots are from VLBI. You see, it's a good agreement, so it's a difference is about 1-2 millimeters. That's why it's, our estimation is quite good. And finally, I added this new estimates to NGSCAD data file. So it's there are 7 values for troposphere delay, first and second, and two for north-south gradients, and for east-west gradients, and for difference for clock offset. So finally, since all the information in data file, we don't need to estimate troposphere at all, and only 3 parameters for each session, for each experiment for clock. So instead of typical number of 1,000 parameters for typical IVS-1 experiment, for a conventional procedure, I've got only 100 parameters here. So actually, I reprocess all observations since 1993, and it was found that formal error for XY pole component reduced by factor of 3 approximately from from 100 microarc second to, so from 300 to 100 microarc second, and also for UT1 minus UTC. So, and I use this method, use all the data to for my global solution, published now in IVS database. So there are about 4,500 experiments since May 93. There are more than 15 million delays, and focusing mostly on the successful reference frame catalog. So what's going on now with formal errors? Black dots show formal errors for ascension and declination for all radio sources in logarithmic scale. Black dots, this is my conventional catalog, and red dots for the new catalog. So that's a kind of improvement by factor of 3 for the most observed radio sources. It jumps down from 6 microarc second to 2 microarc second. And also improvement is seen for, here for all the frequently observed radio sources. What is the effect is coming from? It's from the troposphere. So the left graph shows formal errors with the standard procedure. You see it's a typical pattern here. Formal errors of radio sources with respect declination growth for negative declination. It's mostly because it's made of VLBA objects. So will be a network in the northern hemisphere observing radio source in the southern hemisphere, and at the low elevations. That's why formal error here grows exponentially. And here we have no such distinctive effect. It means formal errors was reduced down, and we've got a global impact on the whole catalog. So it's a just for comparison, rotation between ICRF remain new catalog, just very small values. It means orientation is good. And now I'm going to the scientific drivers, which is desperately wanted here. So it's a form graph plot shows the standard values for secular liberation drift, also known as galactic acceleration. It's for the previous solution. Oh, sorry, this is for official solution from Macmillan paper, what was used for IRS conventions. That's a form amplitude is 5.8 microarc second plus minus 0.3, and my new estimate is a bit lower. I believe it's more consistent to the Gaia solution, and formal error is 3 times better than the previous one. Also, it's improving for the position of vector direction. Also, if we talk about quadruple systematic, it's also statistically significant, but I have no time to discuss it here. Also, hidden systematic about Gaia negative parallax. As you know, Gaia negative parallax was claimed as a 17 microarc second function of magnitude, colors, and coordinates. So in VLBI, it's also possible to model negative parallax. This is very simple equation. So this is here barycentric distance. This is distance to potentially close radial source, and this is analytical model used for partial derivative. I tried to estimate negative parallax. I found its negative parallax exists and statistically significant for 30 years, about minus 16 microarc second, and separated on even other years, it shows more or less reasonable values. My first idea was it's not real. I believe it's natural one. So it's too good to be true. And one potential interpretation was a transparent dark matter, assuming if solar system within a bubble of dark matter, and we've got some lensing effect due to annual rotation of the Earth about solar system. Technically, transparent the dark matter may cause some parallactic-like signal, and analytical model shows it's exactly mimics with signal with negative magnitude, but unfortunately, comparing to the celestial mechanical limits, it's we need 5 magnitudes larger density of dark matter with respect to the limits from celestial mechanics. That's why, unfortunately, I have to rule out this potential explanation. So the next one is about, I try to implement the Gödel metric. It looks good, but I have not enough time to talk. And I believe the most plausible explanation is non-orthogonality of fundamental axis. As you know, all our fundamental axes are ruled by position of radial source. We believe if radial source exactly in the pole and another radial source is exactly along the equator, the angular distance between them should be perfectly 90 degrees. But this angular distance is out of our control. So technically, due to variability of radial positions, it might be not 90 degrees, but say 89 degrees, 59 seconds, 59 minutes, 59 seconds, plus some decimals. So it's non-orthogonality may cause additional problem, and actually I found that it would cause circular motion with annual period. That's why I believe it's a negative parallax effect detected previously. It's not elliptical signal, it should be kind of circular signal with a variable magnitude, because all variation of defining radial source position is variable. I'd like to say this is not only my own result. My colleagues have got detected the negative parallax also with other software, standard procedure, and standard cipher data. So it's not my bug. I believe it's a feature of the catalog. So I believe it's a negative parallax is manifestation of the fundamental axis non-orthogonality at the level of 220 microarc second. We should consider how to deal with that for preparation of the ICRF4. So finally, if we talk about improvement statistically, I believe what we can get by 2027 has about 6,000 radial sources. And I hope we'll get formal error for the most observed radial sources at the level of 2 microarc second. And a realistic flow on an inflated error, I believe, would be reduced, say, Maybe I'm too optimistic from 30 to 20 microarc second. It's kind of my personal wish how to proceed. So I'm going now to conclusions. So troposphere and clock may be calibrated using VLBI data. So it's a kind of self-calibration, similar how we're dealing with ionosphere. So we've got 4,000 or more also SNX data with troposphere and clock calibrated. And if you want, you can get it. So formal errors of the radio source with the most, I don't know, 100,000 observations can be get at the level of 2 microarc second. So we've got a bunch of hidden systematic, known, and new. And in particular, I'd like to point out that the secular aberration drift statistic is improved. So it's closer to the Gaia magnitude and formal error is better. Thank you for your attention.
Do you have any questions?
Oleg, can you clarify? Did I understood correctly? So you took a data set of diagonal terms to 0, then reprocess the same data set, put adding of diagonal terms, and you got improvement in accuracy factor of 3. Is that correct statement or not?
I don't understand what you want to say. I estimated troposphere delays, gradients, and clock offset for each moment. Now I'm using a plain least squares method. I don't need anything. I don't need segments. I don't need collocation. I don't need whatever you like, what's usually used for that analysis.
Please use the microphone for online.
Oh, sorry, I don't need collocation. I don't need segments. I don't need any statistical models. I just using very plain least squares method. So I've got a very simple procedure, and since the number of parameters reduced from several thousand to 1 or 200, I believe it results in improvement of statistic of all parameters estimated for each single experiment. So if anybody wants, I can provide access to all the data files in NGS-FAT. All the variations are there. You can try it. So we try it with WIFs now, and WIFs shows similar improvement with respect to standard analysis. So I can get some plots on my presentation, but I have no time to discuss it too long. Thank you. Thank you.
Sit down, Phil, sit down. Sit down. Okay, it's past. Let's get started on time, finish on time, because I'm such a good timekeeper. That's why I'm going to try and force it on others. Whereas the first talk is, let me get my glasses on, it's an important one about correcting source structure. Namika Moya, to give my pronunciation. Please.
Thank you and good afternoon, everyone. My name is Namakao. Actually wanted to mention that I'm a past data student from Zambia, currently at UP working with John McKean, Alette, and Hannah. And we are working on source structure corrections. So I'm here to present part of our work. I'm a first year PhD student. Okay. All right, so the AGNs that defines the ICRF sources are not perfect stable points. They have some intrinsic structure, and this has been established and identified for over 30 years now. So, and we can see that from the components that contribute to the geometric delay, source structure is not modeled. And some past studies have already shown that source structure can introduce significant errors in VOBA and VOBI measurements. So yes, so we want to correct source structure, and we are doing this for an entire K-band celestial reference frame. Okay. There have been some mitigation strategies that have been that are being used to mitigate source structure, and some of them include selecting sources with less structure, observing using the jet position angle. Okay, Okay, and applying source structure corrections. But all these strategies require monitoring of the quasars because the structure can change with frequency and also time. So we need to monitor and understand what is happening to the sources. Yes, and other people have suggested moving to higher frequencies, as you saw from Chris's talk earlier on. We can avoid some structure when we move to higher frequencies because sources tend to be more compact at higher frequencies. The challenge to this is that we still observe significant structure even at higher frequencies. And because we want measurements that are so accurate, we have to look at how we can work and resolve source structure. Here is an example of a source that has been observed at different frequencies. And on this slide, we observe that we have better resolution and that we have less structure as we move to higher frequencies. Yes, so in this project, we are using two mitigation strategies. We are applying source structure corrections for an entire K-band celestial reference frame, and we are also using a higher frequency, which is K-band at 24 gigahertz. So here is an extract of the imaging campaign led by Alette. So what we see here, Yes, okay, looking for the pointer. So what we see here, the first three in the first row there are compact sources, and generally this is how sources look like at K-band. They are compact, but we see that we have some sources with some bright extended emissions, some sources with second bright components. And the moment that we begin to see these emissions, extended emissions, and some other components, then we know that we're going to have some error when we try to measure the position because of these components. Yes, so we also have sources with triple components, and all those sources, as we see sources with an elongated core, then these can introduce error in astrometric VOBI measurement. Yes, so there have been some challenges in developing a source structure correction model, and we have three main challenges. The first one is that source structure modeling requires ongoing imaging and at the observing frequency. And the second challenge is that quantifying source structure is complex, and this has been brought out by many people who've been working on source structure. Yeah, because it is influenced by many factors, which include relative brightness, separation of source components, and just the diversity of source morphology, as we saw in the previous slide, that we can have different different types of sources. Then the third challenge is that it is hard to connect images from one session to another, since imaging is done on a relative and not absolute scale. So we are looking into this, and look out for Maria and Richard Stokes, which are on multi-view phase referencing. We have three main objectives in this project. Firstly, we want to characterize source structure and its temporal stability for K-band sources. Then secondly, we want to quantify the effect of source structure. And finally, apply source structure corrections directly during VOBI analysis using updated models. And we want to do this using VIVS, the Vienna VOBI software. So in looking at the first objective, we want to characterize source structure. So this project is made possible by the work done by David et al., because they have imaged K-band sources, also doing model fitting and structure correction maps. We also have structure metrics, many different structure metrics that we can use to identify source structure. Here, what we can see on this slide are two different sources. The first one is 0420 minus 414. So this is an example of a source that is good. It's compact, and when you look at the map there, it shows less structure. We can also see from the structure metrics that we have the compactness here. If the compactness is 1, then it means that a source has no structure, or source is compact. Yes, so this is close to 1, and we can see that this is a good source. And whereas the other source, we can see that this source has some structure. We can also see from the image, and there we have compactness at 0.45 and other metrics. Now, we also want to quantify source structure, and in this regard, we started with looking at the source position stability and try to relate it to the source structure. So what we have here is the time series showing the scatter in for all the sources. So here we have a sample of 92 sources. Yes, so this is one of the sources that we want to show you. So this source seems to be stable because we have very few deviations from the 0 point in right ascension and also in declination. And when we look at the images, we can see that this source is compact. So we can use the time series data of each source and compare to the image. And then we can see whether a source is compact or not. I want to show you another example. This is a source that seems to have large deviations from 0, and this is not a stable source. This is 3C418. We can see, even as we look at the images there, that we have a second bright component, which appears and sometimes disappears. Yes, so from the imaging, we can see that the time series is supported by the imaging that we see of this source. So this is a source which is not stable. We also extracted the structure index, and the structure index just shows us how the structure can affect our astrometric position measurements. And if the structure index is 0, then or it's close to 0, then it means that a source is compact. But if it's 4 or more than 4, then we know that a source has a lot of structure. Yes, so we can see that we have those variations, and this also just tells us those variabilities in the source that we talked about. Yes. Then we have another example, which is 1611 plus 343. This is another source that seems not to be stable, especially in declination. We can see that pattern there. You can see that the position seems to be jumping up and down, and it's not a stable source. We look again at the images and we see that we have some second component which is coming forth. And yeah, from those images, we can see that we have some component that is affecting our position measurements. Then we have, and the final objective, we are applying source structure corrections directly to the data analysis. So with this objective, we still have work in progress, and we have put it in our future work. So under applying source structure, we are currently implementing a model to calculate extra delay based on the equations from Patrick. And we're using the clean component models, and we're also testing this using the Vienna VLBI software. So in conclusion, sources seem to be more compact at K-band, though we still see some exhibiting some significant structure. And we have many structure metrics to characterize source structure. And we also say that there is some relationship between source position stability and source structure. So this is what we are working on. In future, we want to also understand the astrophysical components affecting source structure, and want to relate this to the work that Fesi is doing, and she'll also be speaking later on. Yeah, so we are excited to apply source structure corrections to all sources at K-band. Yes, thank you.
Thanks, Peter. That was the first thing I was going to say. Sorry. Do you have any questions? Questions from the audience?
Thanks. I know, Mikhail.
Hi.
Oh, who I am? Okay, I'm Chris DeLulla from the U.S. Naval Observatory. Really nice talk. So can you go back to where you're showing the time series and the images? Any one of these slides. Yeah. So this is something that I've been thinking about doing as well with our imaging. And so it's really interesting to see. I was never fully sure, though, if you could say if it's from the other source, because typically the amplitudes of the jitter is less than a beam in the image. So I'm not sure how we can actually say that it's definitely due to the presence or lack of a second component that kind of comes and goes. I don't know if you have any comments, or we could talk offline. It's just something I've been interested in kind of exploring as well.
Yeah. Okay. I think my comment would be that, of course, with the images, we can see that we also have the image quality, and sometimes it's low, but and that we have many other things that could contribute to the offsets that we see. Yes, but yeah. So we can see a little bit of structure, and then we are also seeing the offsets in the time series. And when we look at, of course, this still needs to be improved, but with what we have now, we can see that this should be as a result of structure. Yeah. But maybe more improvement needs to be. Okay.
It's from Canberra DSN and CSRO. Yeah, so if you plot array and deck in time, I guess you can also plot the position angle versus time. And also, I wonder if you can associate variability with any astrophysics, like a precession of jet or binary black hole or anything.
Oh, okay. Sorry, I think I didn't get that too clearly.
Okay, yeah. All right, yeah, it's
Associated with physical phenomena like the jet precessing, or a new component coming out, or things like that.
Oh, okay. I think I'm not too sure. Yeah. Maybe future work. Thank you.
Any more questions? We don't see Benedict.
Oh, thank you.
Yeah, thanks a lot. Good afternoon, everybody. I'm happy to introduce a new project here as soon as we have the slides up. But yeah, I'm happy to already start talking. It's a project that focuses on improving K-band VLBI, especially focusing on ionosphere corrections and also the scheduling. And it's a collaboration between ETH Zurich, where I'm from, and Hartrau here in South Africa, and the Technical University of Vienna in Austria. So the co-authors and participants in the project are Alet, my PhD students, Marcel, Arno, then my postdoc Matthias, then Hannah from Vienna, and also Marissa. Now let's start. All right, so we are all very much aware of the importance of VLBI for celestial reference frames and the ongoing trend towards going to higher frequencies to improve the astrometric precision. And especially with the focus here on K-band, a very important milestone was, of course, the inclusion of K-band-based celestial reference frame in the ICRF3. And yeah, there are ongoing initiatives to further improve K-band VLBI data, as we've seen in the last presentation, for example. And also in general, there's the Astro to Geo VLBI project led by Alet, who is coordinating activities to further improve K-band VLBI data. And in that context, we have now started a new project, namely COSMIC, which I want to introduce in a bit more detail now. So the COSMIC project stands for K-band VLBI observations with improved scheduling and ionospheric correction. And it's done in collaboration between ETH Zurich, Hartrau, and the Technical University of Vienna. It's funded from a Swiss institution that encourages collaborations between Switzerland and Africa. More details can be found on this website that we have established, but I want just to emphasize the main objectives, which are to, first of all, improve ionosphere corrections that are used in K-band VLBI processing. And for this purpose, we will be using machine learning. And then finally, to introduce some new developments in scheduling, also to the K-band VLBI scheduling. And these will be the two parts of my presentation. Let's first start with the scheduling aspect. Now, there are certain challenges in the scheduling of K-band VLBI data. Currently, it's dynamically scheduled with quite a bit of manual work required to prepare the source lists. And yeah, there are certainly some opportunities to make this a bit more automated and a bit more improved. Also, we are using data from various networks, but certainly a lot of the K-band VLBI observations are coming from the VLBA. But to balance that with also the observations from other stations, especially in the southern hemisphere, is certainly still a challenge. Now, the idea of the project is now to introduce scheduling with the approach based on the software VSHAT++, which has been developed first of all in Vienna by Matthias Schartner and is now continuously improved at ETH Zurich. This scheduling software is based on a so-called brute force Monte Carlo approach. So basically hundreds of thousands of individual schedules are created and then simulated to select the best possible schedule based on certain optimization criteria. And due to the quite successful approach in improving certain parameters like the number of observations and then also the geodetic parameters, it's increasingly being used by the IVS community. And in this project, now COSMIC, we have started the discussions how to best incorporate this scheduling approach for K-band. And the critical thing is here to understand how we can map the requirements and objectives of the K-band observing program to translate that into objective criteria that we can use then during the scheduling. So basically how to optimize the schedules. And these discussions have already started now. But just to give you some indication of what we would expect in the future, we have seen quite a bit of success of applying this scheduling approach in other observing programs, especially in geodesy, demonstrated in programs of the IVS, the International VLBI Service for Geodesy and Astrometry. Here an example from the intensive sessions, so very short sessions that are used to determine primarily DUT1, so Earth orientation. And in this example from the INT 2 and 3 sessions that have been going on for quite a while, which have been previously scheduled with more classical approaches. And then at about the middle of 2020, more and more sessions have been scheduled with VSHAT++. And here you can see a quite visible improvement in terms of the formal errors of DUT1. Since this new scheduling approach has been introduced. And we would expect similar improvements also for K-band VLBI data. Now, this has been optimized for the geodetic parameters like DUT1, but here for the K-band data, especially recognizing the importance for the celestial reference frames, we would actually use the software in a way that optimizes not only their geodetic performance, but also the astrometric and astronomical parameters. This would mean that we have a rather source-centric scheduling approach, which we have, or Matthias has shown in this publication here from where this plot is taken. Basically, here we compare a geodetic scheduling approach, which is here labeled with G, and then different approaches that bridge more from the geodetic to the astrometric and astronomical optimizations. And here we can see that while still quite good performance is achieved for geodetic parameters like the EUP or the station coordinates, also here for the radio source positions, quite a good improvement can then be seen here for the astrometric scheduling approaches compared to the geodetic scheduling approaches. So here these are the formal errors here. And we would think that this would be quite beneficial also to the K-band VLBI data. Yeah, then let's move on to the second part where we focus now on the ionosphere. As you might know, with K-band VLBI data, we only have one single frequency, so we cannot simply correct for dispersive effects using dual frequencies. Hence, we need some external corrections for the ionosphere. And that is typically done with so-called global ionospheric maps, the GIMS, which are providing the vertical total electron content, so how many electrons are in the ionosphere, as a function of space and time. And these are typically based on GNSS data because they have much wider network coverage and much more dense. And yeah, typical approaches to model the VTEC distributions is, for example, using spherical harmonics. And our idea is now to here introduce machine learning. And we have here some first results of applying machine learning to ionospheric modeling. The advantage is that in principle, machine learning is very well suited to capture nonlinear relationships between different locations and also in time. And it can benefit from large amounts of data that we nowadays have from GNSS. And this model has been developed by my student Shuyin Mayo, and will be now further refined for the K-band VLBI observations. Now, the basic methodology here is that we have GNSS data from a network, for example, from the IGS, so about 400 to 500 stations. And from the raw data, we can estimate the vertical total electron content at individual ionospheric pierce points using this single layer assumption. And these data points are then used for the training of a machine learning model. So basically the target of the machine learning model, or in this case, a neural network, are really the different VTEC values. And our features, so the input values for this model are the location and time, basically. And in terms of location, we use solar magnetic coordinate system to reflect the physical changes in the ionosphere. And then also we consider the periodic behavior, namely the daily signals and also the yearly variations. Now, once we have this model trained, we can apply it on any location on the Earth and also at any point in time where we have data for training, and then apply it to correct the VLBI data. And we have now established a pipeline to process this quite in a straightforward manner. So basically going from the raw GNSS data to the machine learning model and then applying that already in the K-band VLBI data. Now, we don't have too many results yet, but I just want to show some preliminary ones where we have applied these corrections and use that to process various parameters like station coordinates and Earth orientation parameters from the K-band VLBI data. Here's just an example of the baseline length repeatability, so an indication of how good these corrections work. And here we compare the corrections from the machine learning model provided by us, ETH, to those from the global ionospheric map from the Code Analysis Center, which are widely used in the IGS community, for example. And here we can see very similar performance for most of the baselines. Here we have results for both left-hand circular polarized data and also right-hand circular polarized data. And for both, the performance is quite similar. More details were presented in this poster by Marcel Eaton, but we will also have this poster online after the conference, so you can have a more detailed look. But we are not done here yet. We want to improve further these models. Here is a list of refinements that we have planned, namely, first of all, regarding the data that goes into our machine learning models. We want to primarily assimilate more data, especially in terms of GNSS stations foremost. In this regard, it's very promising news that all the VLBA stations will have their co-located GNSS receivers operational in the next year. So this will for sure improve the accuracy of this model for the VLBA sites. And then also nowadays, there are many more stations beyond the IGS network that we could use. Also, I think right now, still a quite important error source is the initial processing of the GNSS data. And I think that will be further improved as well. We also want to include data from altimetry and radio occultation, which should improve the performance over the oceans, especially for stations on islands. This should be beneficial. And then also include ionospheric data from VLBI dual frequency observations like S and X. And there was also a poster presented by Arno Rueck. And yeah, it will also be online after the conference. And all these additional investigations are further supported by this project funded by the Swiss National Science Foundation that aims to further improve machine learning-based ionospheric modeling. The machine learning models will also be improved further, for example, for focusing on the input data and how we encode it. For example, we have experimented with a new way to do the positional encoding, which has actually improved the results quite a lot over the oceans. Compute these models over longer time spans and then fine-tune the models, especially for the VLBI K-band sites. And with that, I'm at the end of this overview of this new project, which just has started. So the goal is to improve K-band VLBI data with ionospheric corrections and then new scheduling approaches. We have some first promising results using the machine learning-based ionospheric corrections, and we will further refine them and then later also include the new scheduling software to improve the VLBI scheduling. With that, thank you very much, and I'm happy to answer any questions.
Hi, Benedict. Nice talk. Just wanted to know the global electron density content with time. What's your resolution like?
Yeah, good point. So the animation I've shown was at hourly snapshots, but we could actually provide these at much finer intervals. So basically, we use the original GNSS data and train our machine learning model, but then it's actually encoded in with a continuous function. So we can actually take snapshots every single minute, for example. So this would be possible. Yeah.
Yep. Hi, Benedict. Thanks. Really exciting stuff. I was wondering if you have thought about doing a repeatability study for the machine learning results. So restart the experiment, see, do you get the same results between the successive runs? Because I know sometimes it's a bit of a black box with the neuron, with the networks.
Actually, I should mention, we run the machine learning models not only once, but at least 10 times.
Oh, okay, fantastic.
And then we compute an ensemble. So this should actually give better repeatability, so better accuracy. But also we can determine the uncertainty then, because we can compute the standard deviation between the different runs. And yeah,
fantastic.
Good points. Yeah.
Thank you.
Thanks.
Thank you. Next speaker is Marie Carbon. Telling us what we're doing.
No, I hope not. Well, my name is Maria Carbon. I'm now with Alicante University. There I'm responsible for the IVS analysis center, so I'm the operator there. I'm also chair of IAG subcommission 1.4. So there we look at the consistency between TRF, CRF, and the EOPs. And so well, this is my background, and I hope that it will explain some of the stuff we are dealing with. So, I'm a geodesist, but obviously not all of us actually care about the celestial reference frame. So if you're an engineer at the construction site, and then you're concerned maybe more about that your tunnels that you drill through the mountain meet in the middle, then you're a geodesist, yes, but you do not care about the celestial reference frame. So there is a very small subgroup of geodesists who actually care about this stuff. And I'm here more concerned with two types of us. So the one group is, of course, the ones who are using the celestial reference frame. And here mostly the people who are dealing with geodetic VLBI. And the second group is the people who are using products that come out of geodetic VLBI. And here I'm focusing on Earth orientation and, of course, its theory. Well, I'm with Jose Manuel also involved here in work concerning theory. It's here in Division A. So what's the wonderful thing about VLBI? So we have stations that are given to us in terms of the terrestrial reference frame. We observe sources that are, which coordinates are in the celestial reference frame. And well, to transform each and between those two, in the middle, we have the Earth orientation parameters. So precession rotation, rotation, polar motion. So on the one hand, this is the most brilliant thing ever because we have one technique and we can do all three of these components. However, it's also the bane of our existence, as we have to consider a lot of inconsistencies and stuff that's going on. Just for example, with ICRF3, so when it was produced, the cutoff date was 2018. And at the moment, there we had ITRF 14 and the consistent EOPs 0414. This was the basis for ICRF3. Then ICRF3, 1 year later, it was published and adopted. And the IVS Analysis Center changed to ICRF3, which of course had influence on the new EOP determination. A couple of years later, so we produced our reanalysis for the ITRF 2020 contribution to the ITRF, which was based on ICRF3, the EOP 04, and ITRF 2014. This was then 1 year later, no, 2 years later, we got the ITRF 2020, and we switched to this, which changed slightly the EOP 14. And only an additional year later, we got the EOP 0420. And in theory, every time we change one of these components, we would have to do a reanalysis of everything for the people who actually are interested in the EOPs. Because if you change one thing, you have to change, we have to reanalysis everything. As we see always differences, so they are there. And if differences, we have to catch down where they actually come from. And sometimes we are very unlucky and we actually see a degradation, which is the worst case scenario. So today we are in a very lucky position that we have a lot of catalogs we can actually enjoy. So we heard all about the current ICRF3. So I'm here only looking at the radio parts. So we have SXK, XKA. I did a few years back a combination of all those three on a normal equation level. We have, of course, the predecessors in SX, ICRF1. I'm here using the expansion 2, which has, I think, 100 sources more than the original ICRF1 version, and ICRF2. And one thing that I also did for ICRF3 sources in this case, I introduced a parameterization similar to what we do on the TRF part to actually correct for apparent proper motion. So I will show briefly how we look at. I will look at the data here for this presentation. I will not focus too much on any formulas or too many numbers, just to give you a feel about it. So, let's see, go back. No, it's okay. So these are the celestial pole offsets with respect to the ICRF 2020 and the CO420 a priori. So as you see, we are quite have a large scatter there. So it's typically scattered about 200 microarc seconds. And here I actually selected a quite set of nicely behaving sessions. So it could be much worse. And here you see the weighted RMS when using the ISRF3, which is very typical. To give you a context, so we have the GGOS goals, which on the terrestrial part, it's this famous 1 millimeter with in long-term stability. And if you translate all these numbers into Earth orientation parameters, what we are actually aiming is at 33 microarc seconds. So we have a scatter of about 200. We get a weighted RMS about 90. And one of the reasons, or one way of how we try to improve the scatter that we see, or results that we get, is to improve the models that we have for notation and precision. So the current adopted models, they date back to 2006 and 2000. So just by the two different numbers you see, they are not consistent in themselves. So we have two distinct models for precision, one for precision, one for notation. And intermediate step we want to do, as it will take quite some time to actually revise the entire theory, is to provide corrections to these models. So here you see the light blue line. This is the correction that so the current we have come up with for precision. So you already see it's at a very similar level. And this is actually notation. So we have a very small signals there. Let me just zoom a little bit in. So now what you see here is the black line. This is a moving average. So this is just for visualization, for giving you a better handle on what we actually see. So this moving average is a weighted average over a half a year. So it's quite a lot of smoothing going on there. So here I will now, the only thing what I do here is I only switch between the different celestial reference frames. So all the other stuff is standard IVS recommendation analysis. So nothing else happens. And just to a reminder, I keep those numbers down here. So what you see here, so this is as before, what we get as a weighted RMS. Here's the difference to the, well, now modern ISRF3 realization. So here, the differences to that, and the weighted average that's running. This is for ISRF3 without applying the galactic aberration. So this was a big innovation now with ISRF3, that we also apply a correction for galactic aberration. And you see the impact on the notation parameters regarding galactic aberration. This is the black line that we have seen before. And well, interesting is what we would see. Okay, in the beginning, where we have very few sources in general, the impact of all this differences is quite big. But unfortunately, we see this also in the more recent data, where we would assume a more stable frame. Here is when I apply this correction for power and proper motion. And then here in this case, well, almost no difference to the standard way on doing it. And however, this parameterization allows me to select different sources as datum sources, and this actually makes quite a big difference. Just a reminder, looking at these numbers, looking at these numbers, and keeping in mind that our GGOS goals are 33 microarc seconds. Also, not everyone cares about celestial pole offsets, but a lot of people actually care about DOT1. And here, because this is the primary parameter used for orbit determination. And if you look at the exactly the same number, here again are the differences with respect to the standard ISRF3. And so we have between 7.5 up to almost 9. And just for easy calculation here, I put as an example 9 microarc seconds, which was translated to half a meter of error at LEO orbits, 2.8 geo. And if we go farther to Mars, we are off by 44 meters. If we change one of the components, also all the others changes. So the same, I have to speed up a bit. Can do exactly the same game for the sources themselves. And well, here the offset, of course, between these is when I apply a correction for a bound proper motion. So here, in case of the sources, it's obvious. I also took a quick look at the errors. So hypothesis would be that that the sources show largest variability along the jet, and the jet directions are random, so they have no preference when it comes to sky distribution. So this is here the time series if I plot it accordingly to rate distinction and declination. And yes, we see that maybe there is a movement along this trajectory, which we would expect. If we calculate, if we get our errors out of the catalog, SR3 in this case, and calculate the angle, we get the angle here. If we calculate the same major axis of the error ellipse for the point cloud, yeah, this is the angle. If we weight all the observations, slightly different angle, and this is if we look at the mean position angle of the features out of the Mojave catalog, we get a different angle. What you see, except of the unweighted time series, they agree quite well. Different is, so this is a different source, this is a defining source. Here, two agree very well, and the others not so much. If you do this for the entire catalog, for all the sources, this is what we get. So you see here, Mojave, there is no clear pattern there, but we would expect for the catalogs or for the other sources or estimation methods, there is. Single session very pronounced around 90 degrees. If we introduce a weighting, we have some more at the fringes, and ISRFC again slightly shift more to the edges. And if you look at it, it's here you see it what's happening. So we have very flat orientation of in the north, and in the lower latitudes, they are almost vertical. In the mid latitudes, this is where it gets more mixed, and this is basically due to our observation geometry. Same here for the different catalogs, ISRF 1.2, 2, and 3, very similar. And the same is also true for, here I calculated Vigos. Yeah, you have this very distinct bands where we have Vigos is in green. The population for K-band is around 100, and for XKA, it shifts a little bit to 120. So what do we see? So it's basically, on one hand, it's geometry. So we have heard a lot about our not so ideal station distribution. And the second one is statistics. So here I introduced the combination of all three catalogs, and we see that this feature even gets more compounded. So everything is or centered in the middle or at the fringes. Same can also be seen in the catalog itself. So if we compare those two sources, we would say that, yeah, this source here should have a higher uncertainty than this one, just by looking at it. In reality, it's actually the other way around. And the reason for that is that this source has much more observations than this one. So it's statistics. Conclusions. So although all the ICRFs I have shown you are consistent internally, so there is no rotation between the frames, we see significant differences. And these differences are mainly due to the different set of defining sources. So this is the major difference between those frames. And so these differences are big enough to actually compromise our work when it comes to celestial polar offsets, for example. The arrows, yeah, they do not really reflect physical properties, but more, they are very distinct for every celestial reference frame. And the major factor is here geometry and the number of sessions. And last slide, so take-home messages. So if we change any component, we would have not only have to do a reanalysis to get our correct EOPs, but we would also have to do a reanalysis of all our depending models. So this is in a long term not feasible. And yes, that's it. Thank you.
We're running slightly behind time, so I'm going to have one question and then if you come up. So do we have a question? Well, maybe we'll try and catch up. Thanks a lot.
Thank you. I will be looking a little bit backward in history. Okay. Okay, so let's talk about extragalactic astrometry. Oh. How to move it? I see. Okay. Okay. What is needed for precise radio astrometry? First, probably most important, goal. Maybe it sounds trivial, but if we don't set goal, we may go to wrong direction. We need to have high angle resolution. We need to have unmovable point-like objects. We need to have stable instruments, observations, a lot of observations. We need enough resources and patience. How do we do? So there are two basic needs. First, we need to have a pool of targets or sources for space geodesy. So it requires approximately 200 bright sources, which will be visible at long baselines and uniformly distributed. And we also need a grid of calibrators with approximately every source at a 2 degrees circle, which ends up about 20,000 sources for differential astrometry, space navigation, and imaging weak targets. How did it evolve? So we can put several periods. Advent, first catalog was published in 1971, and accuracy was about arc seconds because of narrow bandwidth. So then astrometry became bad product of space geodesy with the first paper of Chopperman 1986, when we used wideband, we reached millisecond level accuracies. And then was era of wheel-based survey, and on Monday we celebrated 30th year anniversary of wheel-based absolute astrometry, so that's why the IAU made this gala dinner for that specific day. There were three types of surveys: pathfinder surveys, when we look for more sources; astrometry follow-up, so when we with the goal of improving accuracy; and high-frequency extensions for the purpose of getting images in high frequency, and sometimes we can improve positions. So foundation astrometry are observing programs. So today we have 68 observing programs dedicated for astrometry, 1,088 observing sessions, which approximately correspond to 2 years of non-stop observations, 62 petabyte of voltage data. Now, I didn't handle this data, but 127 visibility data I have to handle. It's about 15 kilograms. I have to use backpack when moving from one side to other side. It took a lot of efforts to process this data, about 4.5 years of just wall time for range fitting. So how do we process this data? So first, we're estimating source position, station model, EOP as global parameters in the accumulative mode. that eliminates many issues which Maria mentioned today. Also, we're using fuse group delays when one band is missing. So when one band is missing, for instance, we have dual band observations, and upper band is missing because of non-detections or because of the RFI. So we can tune our atmospheric model for that sessions and the compute uncertainty of atmospheric contribution and use this data. So we also have to use advanced data reduction models. We'll go well beyond IRS convention. We're also running auxiliary single band solution, and we're implementing in cascade of reweighting and for counting for red noise. Where we are now. So this is the result of this 30 years effort. So we have 21,907 observations of sources rather uniformly distributed over the sky. We still have less sources in the south hemisphere, but that's just because of disparity on the instruments. But what are errors of the errors varies in 4 orders of magnitude. So here I put plots of cumulative fraction for semi-major and semi-minor axes. And on the right-hand side is the zoom of that. Very important to account red noise impact. When we can get, it has become rather customary in space geodesy for last 20, 40 years to report formal errors. And we all know that formal errors provide you minimum. It's a low possible errors which can be in practice. Real errors are always bigger. So, accounting for red noise and red because of color of blood, it gives you different perspectives. So for red, this is different estimate of red noise of error flows, about from 60 to 100 microseconds for red session. For declination, it is from 100 to 200 microseconds because of impact of troposphere power delay. This was rather unpleasant. There was many times today was mentioned ICRF3 catalog, so I put just prepared slides. What is the difference? So we use much more observing campaigns. I'm working for NASA, and NASA has 4 core values, and one of them is inclusiveness. So in this approach, we include all the data from for all the sources. We're very open, so we don't have closed door meetings. So data from all observing campaigns, whether this was whether we are PI or RQI, whether it was run by our friend or just a colleague, all data from all the bands, no data point left behind. And you see the fruits of this approach. So we also paid a lot of efforts for photometry. So we have 122,000 images, sort of more than in my hand. I say I'm not a bald guy. But let's go further about error budget. So this very approximate breakdown of major error sources per writer session declination. So we approximately equal 50-70 microseconds per component. Tropospheric errors affects all band data. Atmospheric contributions affects only K band data. Some structure affects probably X band greater than K band. At least so far, we don't have evidence of the opposite. Let me talk more about K band versus SX or SX. So we see from analysis of SX data set versus GIM, so we can derive that errors of atmospheric contribution K band from GIM. And on this plot, green line showed what is distribution of arc length SX versus K when we do not account for this atmospheric noise, and the pink line shows what we account. So we see that accounting for that red noise, we can get much statistical agreement for this data. And here there's another for the manifestation of the systematic errors we see when compare K-band SX, we see declination errors. So then the conclusions for K-band astrometry is not competitive with respect to S6 SX. impasse. If somebody think that going to a higher frequency, you can get high accuracy. Well, if you believe in white noise, maybe red noise puts the limit, and limiting factor is atmospheric contribution, much more complicated than we used to think. How large is source structure contribution? Can we see it? Yes, we can see impact is comparison of dual band versus K band. We see this is versus jet direction, and we see the peaks, so that generally differences are greater along and opposite jet directions. We can get quantitative measures. It's approximately the same as an contribution, which gives the increase in errors along north direction. But level is about 100 microarc seconds. Let's look at how generally look source structure, how big the source structure. This is differences SX versus K band, and in the case if there were no effect for source versus jet direction, in the case with no source structure contribution, that distribution would be perfectly uniform. We see slight elongation, so this ellipticity of that distribution gives this a manifestation of source structure errors. We said on average, and this critical word on average. We know examples which goes order of magnitude high, but on average, it's about 100 microarc second. Let's go to Gaia. So we have almost 13,000 matches between VLBI and Gaia. So here I put this distribution of normalized arc differences, and black curve is for reference relay distribution, and green point what is the current. And this gives good feeling about our validity of our error method. If you have good eyes, you may see pale pink point. It was we had 6 years ago. We see some improvement, still not perfect. We can look at in more details, and if we split Gaia data in the three subcategories with these small isolated them medium and high, we see that at the green points, about 40% of the point has a close distribution to relay. This indication that at least in part this deviation from the relay distributions is due to Gaia errors. What is more precise, VLBI or Gaia? Well, differences, median differences, approximate factor of 4. For Gaia 44 beta. Well, this is because of we don't have too many observations for VLBI to get this level of accuracy. Can we see VLBI systematic errors? So this is a diagram of position angle with respect to north. So there's many colors, but let's say green this as is. But we can separate data on several bins depending on number of observations. And the black point, if we put more than 120 observations, and they see the black point, this peak on the 180 degrees almost disappears, and the peak at 0 degrees becomes smaller. So it is confirmed conclusions which Marie made 10 minutes ago. Yes, we need more observations to beat this kind of systematics. Can we see Gaia systematic errors? Yes, we can see this similar diagram, but with respect to jet direction, these are peaks, probably the most famous results of Gaia for intergalactic astronomy. So there's manifestations of this optical structure which goes along the jet. Are Gaia systematic errors stable? Gaia is sensitive to centroid, so it is contribution core jet. So if there's a brightening on the core or brightening on the jet, so that centroid will move like with these two guys. Some will be stronger after having good lunch. He will move one direction. Do we have evidence of that? This was predicted. Basically, this expectation of there will be jitter we published before we were able to measure, and when was Gaia data release was to publish, we can detect this. These proper motions. You see these peaks of proper motions, those which are significant for some level, along and opposite direction. You can see a similar peak at VLBI, but the devil is in detail. So VLBI is approximately 2 orders of magnitude smaller. And AGNs move tangentially. This is manifestations of variability of the optical structure in Gaia, because one of the components, jet or core, becomes brighter. And Summary. Each technique has its own detectable systematic errors. Comparison reveals that morphologies at scales below the Pontryagin function. And this is why it makes this comparison of different frequencies very useful for astrophysical studies. From other side, chromatic morphology sets the limit of frequency-dependent astrometry. Thank you for attention.
Any quick questions?
Just a quick comment and thank you. Your 20,000 source catalog is extremely useful for finding candidates for all kinds of projects. I know the imaging community uses it quite a bit. So I think you're the only ones really pushing catalogs up to that number of sources. Thanks.
If there's no more questions and we're running behind schedule, perhaps I'll invite Luke to come back.
Okay. Let's wait for the slides. Yes. So I am Jiacheng Liu from Nanjing University, China. So in this talk, we will walk out from the radio band and to infrared band, discuss the future infrared reference system. Maybe it will be also very useful. Yes, thank you very much. And my talk is about the all-wise catalog as an infrared reference frame in Gaia era. And here is the content. First, I would like to talk about fundamental reference system and the infrared observations. And the second, I talk about astrometry of all-wise and Gaia DR3. Of course, they are quite different. And third, we detect the internal systematic errors in all-wise catalogs between stars and QSO-like sources. And also I talk about future multi-wavelength reference system. And everybody in this room is familiar with Gaia CRF3. It is realized by more than 1.6 million extragalactic sources. But in optical band, the right figure shows the number of Gaia CRF3 sources and ICRF3 in radio band. Okay, why we need an infrared observation? Importance of infrared observation is of course important, and why we need a reference system? Because we need to, for example, to fit the orbit of some stars and to detect exoplanet for dwarf system, and also the structure of our galaxy. We need to study Bulge and Bar because it's suffering heavy interstellar extinction. So the infrared band is much better. And we have also, now we have some infrared astrometry. For example, the Dennis database in 2003, it is not an all sky survey, but in the southern sky. It covers 3 bands and the limiting magnitude is about 18.5, 16.5, and 14. And more famous one is the 2MASS point source catalog. It contains 470 million sources, and for the main scientific goal is for large scale structure of the Milky Way and the local universe. And the limiting magnitude for JHK is the 17.1, 16.4, and 15.3, I think. And the typical position accuracy is 80 mass. But no proper motions are available in this catalog. And now we have the better catalog called All-Wise. It is an extension of WISE mission. It is a space mission. In the telescope moves in near Earth orbit from 2010 to 2011. And it is equipped with a 40-meter telescope operated by NASA. It has four bands, W1 to W4, and the number of sources are very large, more than 747 million objects. And here is the basic information for the All-Wise. It is a candidate, now the candidate for the infrared or sky survey can be used as an infrared reference system. The main observational epoch is about 2010. It is quite near with Gaia. And it has the big advantage is that it has apparent proportions. It has improved astrometric accuracy because it used two mass as reference reference frame, and it also used the proportion from UCAC4 to transform the basic epoch. Okay, here the motivation is to find out systematic and apply necessary adjustments to all-wise for well-behaved infrared reference system, which can fulfill the requirements of the ICRS. The cross-match between Gaia DR3 and the all-wise data has been done by Gaia team. Thanks to their excellent work, we can get cross-matched data directly. Here is a number of sources, and we also use only extragalactic sources or AGN. AGN, it's about half million sources. They are treated separately because extragalactic sources are used to define basic reference system. Here is the distribution of all sources and quasars. And here is this is astrometric properties of common sources. You see that the Gaia observations is much more accurate than the infrared observations. This provides us a very good basis to compare the Gaia and the infrared catalogs to find out the systematic index. And here is this also shows the uncertainty in all-wise source catalog. For the left for position and the right for proportions, you can see that all the quasars are in general more accurate than all sources. Yeah, and in the bottom we plot the relation between the position and the proportion errors with respect to W1 magnitude and W1 minus W2. Only W1. The left one is for position alpha and delta. For position errors, and the right is for promotions. And here is the difference in components of positions and promotions. The first one is for position delta alpha and delta delta. It is a differential coordinates between Gaia DR3 and all-wise. The right is for promotions, and the blue dots are all for extragalactic sources. And here is the some statistical information for the differences for delta alpha, delta delta, and delta mu alpha and delta mu delta. And we also checked the normalized difference for both for components and for normalized angular separations. You can see that if the errors in alpha delta are obey normal distribution, and so this will lead to that the normalized angular separation should obey the Rayleigh distribution. But you can see, but you can see here it does not obey the standard Rayleigh distribution clearly, because there is a long tail in this part. This shows that there are systematic errors in the all-wise. Yes. Okay. And how to describe the systematic difference? We use the magnitude and color equations. Here you can see the position and proportion difference with respect to the W1 magnitude and the W1 minus W2 color index. We can call it color index. Here the 6 dots are the moving average of the differences. You can see that there are no strong systematics as a function of W1 or W1 minus W2. And another way to describe the global systematic is using the VSH. You can see here here the figure is for the zonal and global difference in different areas of the celestial sphere. We divided the celestial sphere into equal area using Zenobie markings method, and it can also be done using another method, I think. Here you can see that here the proportion has very large systematics here, and also for positions. And these two figures are for all of the sources, which means 570 million sources. And we also have the position difference for quasars. They are quite different. They are quite different, not as the same pattern. For quasars, we do not consider the proportions because generally we consider that quasars do not have apparent detectable proportions. Yes, then we calculate the global difference between these two catalogs. One is in optics for Gaia DR3, and the other is always in infrared. And here R is the global rotation, and G is the glide vector. Here is the main results. Here is all sources and QSO-like sources. We also tested if we limit the sources to smaller angular separation and to brighter magnitude, but the results are quite stable. So, but you can see for all of the sources, most of them are stars, of course, and for extragalactic sources, the R and G are quite different. So we think there are maybe the geometric properties in this catalog for stars and the quasars are different. So how to calculate the internal difference between stars and quasars? Because they are in the same catalog, it is difficult to find out them with only one catalog. We use Gaia catalog as a standard because for Gaia, stars and quasars are uniform they are in the same reference system. And finally, we detect that in this all-wise catalog, the stars and quasars are in different reference systems. Their difference, the global rotation and glide are estimated in here. The magnitude is about 10 mass and 13.7 mass for global rotation and glide. Okay. So in the previous part, we detected that stars and quasars are in different reference system, but it is difficult to calculate the internal systematics with only this. We need another standard that is Gaia. And we also measured the galactic plane in the Gaia reference frame using the all-wise catalog. You must remember that in Division A meeting, there is a talk about redefinition of the galactic coordinate system. I think it is in the working group of numerical standards. I think we have already done some work in this for this problem, and using the all-wise after we correct some systematics and to adjust the catalog to the Gaia reference frame, we find that the inclination of the galactic plane with respect to the equator is about this value. The inclination of the galactic plane is about 0.5 degree larger than the Hipparcos value. Maybe this will be used for the redefinition of the galactic coordinate system. Okay, this is the conclusion. And I think an infrared reference frame is needed to fill the gap between optical and the radio band reference frame. And we detect as a first try, we detect global orientation and glide in this all-wise catalog. And what's in the future? We plan to do similar work using the updated CatWise 2020 catalog. It is the most recent all-sky survey in infrared band. Because we have no cross-matched data. In fact, we have already done cross-matched and we will have more results in the future. And I think everybody is interested in the future infrared reference frame realized by the Gaia near. The distribution of sources are here and has better error propagation to the past and future than Gaia. Okay. And in China, we plan to launch the China Space Station Telescope, CSST. It is a 2-meter telescope designed for extensive sky survey mission. It is wide field of view and high image accurate. It has 7 bands from 255 to 1000 nanometers and covers about half the full sky, and the limiting magnitude is 2026. It is also very promising. A very promising sky survey in infrared band. Here is a simulated number of quasars in the density of quasars if we reach 26 magnitude, and the predicted accuracy in the future. Also, maybe we need other bands, referencing other bands, but I will not talk it too much. Okay, thank you.
So questions?
Yes.
Well, I had one. I was
Yes,
going to ask
okay.
you whether you thought you could deal with these systematics. You isolated them, identify them, can you remove them?
Yes, if we identify them with high confidence, we can remove it. Then because Gaia is a quite good standard, we can move the infrared to that standard, and then it can be done. I think
that's future work. Yes.
The future work is to use the first step is all-wise, second step is cat-wise 2020. Okay.
So which of Gaia wavelengths or infrared are supposed to be coming from more inner part of a supermassive black hole? Do you expect any? So what's the difference between Gaia detected emission and infrared? I mean, in terms of source position, yeah. So do we expect
between Gaia and
Gaia stellar and Gaia quasar?
yeah, I mean, yeah, that's right. Yeah. So
you mean the difference between
is there any advantage
stars
for
and quasars detected by Gaia?
I mean, yeah, in terms of proximity to supermassive black hole, yeah.
The Gaia detect stars and quasars with the same method, I think, and in the future it will not change. I think.
Yeah.
Yeah, where does the optical come from relative to the infrared?
Yes. Okay. It's cross-matched. We cross-match the data Gaia and the infrared catalog, and to calculate the difference in coordinates, then we have the positional difference or motion difference. Did I answer your question? Okay. Okay, thank you.
So now we're going to position of time.
Okay. So this presentation is going to be quite a change of pace from the other papers you've heard today. And it's motivated by the fact that everything moves. So when you make an astrometric observation, you want to tag it with a timestamp. And the question is, how accurately do you need to make that timestamp so that it's not the limiting factor on your observation? Obviously, things that move very slow, you don't need to know the time very well. But if something moves very fast, you need to know the time very accurately. And that is what I would like to address today, as soon as the slides come up. So, I work in the area of near-Earth asteroids, particularly those that are hazardous to the Earth. And when they get close to the Earth, they can move very fast. So we make astrometric observations using optical telescopes, and we need to tag those observations with a time so that you can compute the orbit accurately and determine, is it going to hit the Earth or not? Okay, there we are. So here's a sample observation of a near-Earth asteroid, 2020 DW. That exposure was taken on February 19th, 2020 with the University of Hawaii 2.24 meter telescope on Mauna Kea. The asteroid is the dot smack in the center. It was 19th magnitude at the time of the exposure. And the whole field of view is about 14 and a half arc minutes. And we had 89 Gaia DR2 reference stars in the full frame. What you're seeing there is like a 5 arc minute subset of the full frame. So those 89 Gaia reference stars gave us an astrometric solution that was good to 8 milliarc seconds. Okay, it was a 15-second unfiltered exposure. So we achieved a signal to noise ratio of 31, and the seeing was about 1.1 arc seconds. So the centroiding on the asteroid itself is good to about 600ths of a pixel, which corresponds to about 26 milliarc seconds. But the key point here is that it was moving 2.66 arc seconds per second. So the time must be known to better than 100th of a second in order to not have the time be the limiting factor on the quality of the astrometry. And it's also worth noting that if your clock is wrong, if there's an offset in your clock, you can take as many observations you want, and it's not going to improve the situation because it's a systematic error, not a random error that you can beat down by root n. So time errors are particularly annoying. Okay, so a lot of asteroid astronomers rely on the clock in the computer that they use to control their camera. And I have seen occasions where the software that synchronizes the clock to, network time protocol, that can fail silently. And so you could be sitting there thinking that your computer clock is correct, when in fact it has drifted off and you don't know by how much. But even if the software is running, here are some interesting questions. When was the last synchronization performed? It doesn't always happen continuously. And how is the synchronization done? If it finds an offset in your clock, how does it fix it? Does it do a stair-step discontinuous correction, or does it just slowly adjust the drift rate so that it brings it back in slowly? If you don't know, you can't say how accurate your time is. Sometimes they will query multiple time servers, and there'll be some scatter in the results, and you need to know how much scatter there is to say what the accuracy of your clock is. But even if your clock is perfect, there are problems such as what's the latency between you when the computer reads the clock and when it sends the command to open the shutter. Even if there's zero latency between those two, there's still a delay between when the shutter starts moving and the field of view starts getting illuminated. And then, of course, there's time for the shutter to traverse the field of view. The camera that we use has a two-blade shutter design. So when the exposure starts, one blade moves up, and then when the exposure ends, the second blade moves in. And then in the next exposure, it just reverses. That assures uniformity of exposure over the field, but as you can see, the time is different for one edge versus the other edge, and then it's just the opposite difference on the next exposure. So one way to solve this problem is to actually measure what your clock error is. And the way to do that is to look at an object that's got a known ephemeris. And the better the ephemeris, the better the time will be known. Because you can compare the position that you measure with the ephemeris position and see what the corresponding time would have been for where you measured the object. You could do this with main belt asteroids. except that they don't move very fast. And so you're not going to get a very accurate time calibration using a main belt asteroid that happens to be in, the numbered catalog. Some people use geosynchronous communication satellites. They move 15 arc seconds per second. That doesn't help us because geosyncs move east-west and our shutter moves north-south. So we wouldn't see a time offset in that case. So instead, we rely on GPS satellites. They move anywhere from 15 to 40 arc seconds per second. So if you can do astrometry good to just 1 arc second, you can figure out what your time is to a 40th of a second. We can actually do closer to a 10th of an arc second, so we can get the time to something more like a 400th of a second. Okay, so here are some tools that you can use to actually do this. Bill Gray has a website called Project Pluto, and he provides all the tools you need to do this kind of thing. So you can input the time that you want to do your observation. You can put in your location, so it removes the parallax. And you can set your minimum altitude and sort order there, a variety of ways to sort the output. And there's the output for the time that I just put in. So you can see a whole bunch of GPS satellites are available to observe at any particular time. We do our observations in twilight. We do a satellite in evening twilight. We do a second satellite in morning twilight. That way it doesn't really take any time away from our science program because the sky is just too bright in twilight to do most near-Earth objects, but the GPS satellites are plenty bright. They're like 11th, 12th, 13th magnitude. So you can do them in twilight. And let's see, you can see here the rates of motion extending all the way up to 40 arc seconds per second for the one that's highest in the sky. Okay, so here's a sample observation. You can see this is a composite of 7 consecutive exposures, and you can see these streaks moving across the field of view. In this case, it's going from south to north. Those are half-second exposures, and the readout time of our camera is about 3.5 seconds. So we have a cadence of about 4 seconds. So what we do is we point the telescope at the position that Bill Gray's tool told us the GPS satellite would be at, and we just start taking exposures about 12 seconds early and watch it drift across the field of view. In this particular case, this observation was made in morning nautical twilight about 29 minutes before sunrise. And you see there's a good number of reference stars visible in the image that we can use to do the astrometric calibration. Okay, so back to Bill Gray's Project Pluto website, more tools. Once you have the astrometry done of the satellite, you can dump them into this tool, and that's what I'm showing here. Here's the astrometry that we did. We've got the computer's timestamp, and we've got the measured rise, ascension, and declination in decimal degrees. And he will spit out for you this output. So here's the input data on the left, and then on the right-hand side here are the residuals. Instead of the usual right ascension declination residuals, he has rotated them into the cross-track direction and the along track direction. The cross-track direction, the residual is given in arc seconds, and the average cross-track here is 0.04. We're doing astrometry to 0.04 arc seconds, and the scatter is about 0.04 arc seconds. So pretty good cross-track residuals. The along-track residuals are given in seconds. This is telling you the difference between what your clock said it is and what the GPS ephemeris said the time is. And I should probably point out that if the GPS satellite ephemerides weren't known really well, the system wouldn't work. So yeah, GPS satellites are providing an extremely accurate time for you. And in this particular case, let me back up. Positive along track errors mean your clock was behind the actual time. And in this particular case, this is exactly what we'd expect. There's a delay between when the clock was read and when the shutter started illuminating the field of view. And you can see that it alternates from a small value to a large value as it goes across. So let me show you the analysis here. Okay, so we managed to get 7 exposures within our 14.5 arc minute field of view. And the second column there shows the Y pixel coordinate for the odd numbered exposures. And for the even numbered exposures, it's the complement of the Y pixel coordinate because of this bidirectional shutter design. And this is the observed time delay that came out of Bill Gray's tool. So I do a linear least squares fit to those two, and we can compute then from the linear least squares fit what the time delay was, and that's this column here. And here's the residual in seconds, the units of seconds. So you can see we've got the time down to just a couple milliseconds. I guess that's the biggest residual there, 2.5 milliseconds. And just some other statistics here. The shutter blade is moving at a rate of 15.7 pixels per millisecond. It took 0.134 seconds for the shutter blade to traverse the entire field of view. And at the center of the chip, we have a delay of 0.168 seconds, and that's good to about a millisecond. Okay. Remember at the beginning when I showed the picture of 2020 DW, I said we need to know the time to better than 100th of a second. If we had just used the computer clock and if the asteroid was close to the center of the chip, we'd be off by 0.17 seconds. So using this technique to calibrate the time really, really comes in handy. So how well did we do? Here's the orbit solution for that asteroid. A bunch of observations made by survey telescopes and some other follow-up observers. We happen to be the last ones to observe this object. One of the reasons it was moving so fast is because it was flying past the Earth. 2 days later, it was 24th magnitude and fading away rapidly. So we were the last ones to observe it. You see the date here, 2020, February 16 through February 18. Then we got it 1 day later on February 19th. T12 is our station code out in Hawaii on the Big Island. And these are the right ascension declination residuals in arc seconds. And I said that the astrometry, the centroiding was good to 26 milliarc seconds, and the residuals are perfectly consistent with that level of noise. Okay, so mission accomplished. Let me also mention there are some fringe benefits to doing this. If you move your observing location by 1 meter with a GPS satellite at 20,000 kilometers away, you introduce 100th of an arc second of parallax. So you can actually use this method to constrain where your telescope is. If the satellite is overhead, that'll constrain latitude and longitude. If the satellite is low in the east or the west, you'll get latitude and elevation. If the satellite's in the north or the south, it'll constrain the longitude and the elevation. And that turned out to be fairly important because when we were doing all of this and testing Bill Gray's code, we kept seeing systematic errors. We're going, what is causing this? We eventually came to the conclusion that the telescope must not be where we think it is. And so we kind of modified Bill Gray's tool a little bit to allow for to move the telescope around. And we discovered that our telescope was 4,244.53 meters above the WGS 84 reference ellipsoid. We had been using a value of 4,213 meters above mean sea level. So different reference frames there. You really want to be using the WGS 84 reference ellipsoid, not mean sea level. So we did not know that, and that introduced a 31 meter error in the position of the telescope, 0.3 of an arc second of parallax for something that was lower in the sky. High in the sky, not so much. But in addition to that, if you compare our best fit longitude with the results from the aerial survey that was done back in 1996, we see that the telescope is 2 meters northwest of that position. We've detected motion of the Pacific plate, 20 years worth of plate motion. So fringe benefit there. Okay, thank you.
time. Do we have any questions? We are already talking
Thank you. You know, we are controlling QT1 minus C2C to keep it within 1 second of time. If we stop the practice in QT1 minus C2C would be high 2 or 10 seconds. Will it cause any more trouble for you or not?
So I didn't quite.
The time was out by 10 seconds. Would you be able to cover that?
If we're off by 10 seconds, we need to know the time good enough to capture the images of the GPS satellite. So we start 12 seconds early, we end 12 seconds late from the predicted position, because it depends on the size of your field of view. The bigger the field of view is, the larger the time area you can accommodate. The slower satellites, you could get more exposures, and you would have to start a little bit earlier and later to capture all of those. It depends on how fast the GPS satellite is moving. We were using one of the G series, the US satellites, on this particular occasion, just because of where it was located in the sky. And so we went from minus 12 seconds to plus 12 seconds. So a 10-second error, we might get one exposure. With some of the other, there was one satellite that was only moving 15 arc seconds per second. That we could probably start 24 seconds early and end 24 seconds late, and then we might get 3 or 4 exposures. So a 10-second error, that's kind of big, but yeah.
We have already used half the coffee break. So if people who need coffee more than anything else should go, if there's one more question.
Okay, thank you.
Overview is 3:30.
I'll try to stick to it, but we're also already a minute behind. Is Sergey, are you there?
Yes, I'm here.
The first talk is supposed to be remote.
Yes. So
Okay.
should I share my slides?
Well, okay, we see you. And we see your screen, and there are your slides. Okay, my name is Lucas Hunt. I'll be chairing this session. First talk is Sergey Kleiner talking about Gaia, VLBI, and
Yeah, thank you. Hi, everybody. I'm Sergey Kleiner from Dresden, Lorman Observatory. I'm supposed to make a review of modern astrometry. It is a tricky business, especially in the middle of astrometrical meeting. So I will try to do this. Certainly, this review of modern astrometry will be biased by my own work, which is actually Gaia, but I will also do something else. So you all know what is astrometry, but let me just repeat. Astrometry is the art or science, as you wish, of measuring the stellar position on the sky. And this is one of my favorite slides whatsoever, showing you the accuracy of astrometric observation, of positional observation as function of time. So we know that astrometry is the oldest part of astronomy, and it started more than 2,000 years ago with the publication of Hipparchus, who published his catalog. And then generations of astronomers observed with naked eyes, with telescopes, and this gives us, in this logarithmic scale, more or less a straight line, more or less, up to the last catalog, which was created using ground-based observations, FK5. And after that, we had a sort of revolutions in two steps. So we went to space, and also more or less in parallel, we have got VLBI, genetic VLBI with also very high accuracy. So we call in Gaia, we say in Gaia many times, so Gaia has done a revolution, or is doing a revolution, and this revolution, what it means actually. So compare it to the previous results, which if you compare to Hipparchus, Gaia observes and provides results for 20,000 times more objects. And for all these objects, about 100 times more accurate as it was before Gaia. So now we are talking about the accuracy of 10 microseconds and even below 10 microseconds. Now, why to bother with all this? Actually, it is very boring for many people if you just say, we are observing the positions of celestial objects on the sky. And well, yes, you can like this, but it is not obvious why it is at all interesting. Of course, for you, expert in astrometry, it is very obvious why we should care about improving accuracy of astrometric observations. And this is because measuring the positions on the sky, we are not measuring only the positions. The positions are by definition time dependent. And from this time dependence, you can decode not only the positions at some moment of time, but also the motion of the objects in space, or at least on the sky. So you decode to proper motions and parallax. And parallax gives the distance, and the distance is one of the most important and most difficult things in astrometry. And that is very important for many parts of astronomy to know the distances to the objects. So using this technique, so observing the trails, the stellar trails on the sky with very high accuracy and sufficient time resolution, Gaia has delivered a lot of new results, and you have certainly have seen impressive results. You have seen certainly this poster made by ESA showing the main results of Gaia from data release 3. And this is, 1.8 billion sources with 1.5 billion parallaxes and proper motions, 1.6 million quasars, basically, extragalactic sources, and more. So the colors and the brightnesses and so on. So recently we have celebrated Gaia anniversary. Gaia is in space now already for more than 10 years, and in the middle of December, we celebrated 10 years of Gaia in space. So here, for those of you who are not in Gaia, or maybe not too close to Gaia, this is the fairing logo of Gaia, so made 2012, basically, or 2013. And this is a child trying to touch the stars on the sky. And many of us in Gaia were shocked to realize that this child is now around 16 years old. This is a very emotional thing for us. Now Gaia is doing very well. Now is this day, the number of days in science operations. And here you see this impressive number of observations which Gaia delivers. So 2.5 trillion of astrometric observations. Gaia's life is limited, and Gaia will stop observing early 2025. It is only 5 months from now. But this will be by no means the end of Gaia as a project. Now, this is the current state of uncertainties of Gaia. And you see the parallaxes and proper motions here. And the color distribution are actual uncertainties in Gaia data release 3. Sorry, this is a misprint. Data release 3. And the white lines here, this is the median. And you see, it depends on many things. It depends on the magnitude, first of all, but also there are some bad examples where Gaia observed too few times and so on. And now these two lines, the solid line and the dashed line, are data release 4 and data release 5. So data release 4 will be based on 5 years of data science and will be delivered not later than mid-26. And data release 5 will be based on all the Gaia data, 10 years of science data approximately, and will be delivered not earlier than 2030. So both these releases, data release 4 and 5, will give us many new, the whole community, many new products. For example, epoch astrometry. Up to now, you had only positions, proper motions, and parallaxes. Now you can do this yourself from the positions observed by Gaia at a certain moment of time. Now, Gaia is a big success, and Gaia, so this big success can be measured in different ways, but this is one nice way. So the number of referred publications using Gaia data is 5 papers per day, 5 papers. So now we have over 10,000 peer-reviewed papers based or used Gaia data. Now, and in this sense, Gaia is used more than Hubble telescope, for example, which was acknowledged by the science director of NASA back in 2022. So astrometry, Gaia makes astrometry more visible for the community, and astrometry as a whole should use actually this momentum to get more attention, more appreciation, and more funding, of course. Now, Gaia is a great thing, but it cannot do everything alone. We need other astrometric projects. These are the limits of Gaia. First, the sensitivity, only to 21. It is almost 2 billion sources, but we should go deeper and we need larger telescopes, ground-based or space-based. like LSST or Hubble Space Telescope or James Webb or Roman or Euclid. We will speak about this a little bit later. The precision, so the ultimate precision of Gaia is 10 microsecond or slightly less than that. But can we go farther? Yes, with at least with interferometers like gravity or differential VLBI can also do this. A resolution, Gaia has limited resolution of 0.1 arc seconds, and we should, in many application cases, go deeper, do better. So we need adaptive optics and space telescopes and interferometers. Again, VLBI and gravity are very good examples here. Larger baseline. Gaia has only 10 years of data. This is, of course, incredible. It was planned to have only 5. Now we have 10. But archival data can be used to increase this 10 years even further. We can use also Hipparcos. We did this for data release 1, for example, and it still can be useful to some extent. Soon we will use Gaia itself as archival data for the future missions. And here LSST and Gaia Near are examples of what can be used, and not only them, of course. Wavelengths. Gaia is purely optical, going to 1 micrometer, but infrared and radio instruments and interferometers are needed and are interesting also. Again, Gaia Near, Jasmine, James Webb, again, multi-wavelengths, VLBI and SKA, and so on. Now, astrometry needs external data, and we, in astrometry, we need external data which cannot be delivered to full extent by the same instrument with which we are doing astrometry. So radial velocities are needed for astrometric modeling, and Gaia delivers those radial velocities as well, but only for the bright sources. And spectroscopic surveys like those I mentioned here are very important. Now, so just to mention a few things which you have heard or will hear, Jasmine. You will hear a full presentation of Naoto Gouda tomorrow. This is Japanese astrometric satellite mission for infrared exploration, Jasmine. This is a real JAXA mission which is going to fly 2030 and will measure in near infrared about 120 stars in the direction of galactic center. Gaia Near is a proposal still. It is not accepted mission, but it was very positively reviewed by ESA several times. And the idea is to repeat an improved Gaia in infrared and add, of course, some additional things. So going to infrared, we can measure 10 to 12 billion stars, so 5 to 6 times more than Gaia did. David Hobbs, who is the leader of this proposal and the whole this business, will give a presentation tomorrow again. And here, for 2 billion of stars common with Gaia will be used as priors, so as archival data, and we will get a combined solution between Gaia and Gaia Near, improving the accuracy, at least of the proper motions a lot, but also of the parallaxes. Now, go fainter. Vera Rubin Observatory or LSST. I don't know if all of you have heard this very impressive presentation of Ivezic at the Division A Day last Friday. The first light is already 2025. It is next year. So this is a big telescope which will observe astrometrically 40 billion sources and solar system objects and alerts, and will provide 1,000 observations for each object. Of course, it is ground-based, but it will deliver astrometry. And you see here the astrometric accuracy of LSST. LSST will also use Gaia to calibrate itself and check their own algorithms. These are all simulations, of course, from 2012, also for Gaia. But let us hope that these simulations will turn into a real accurate catalog with this accuracy. So we will go much fainter to 25. Okay, now small field astrometry, gravity. It is a great instrument with accuracies between 20 up to 20 microseconds, with a very small field of view, and you will see the presentation of Sylvester Lacour tomorrow on that. Then we have, it is already working, and we are actually calibrating each other in one way. So with Gaia, there's some collaboration. And there is several proposals for small field astrometry in space from Fabienne Malbé and Céline Böhm and many other people. And you see here, so with very, very careful metrology, the people claim we can reach the 0.1 microsecond from space in small field astrometry. Now, an interesting question, what's about non-astrometric space telescopes like Allwise? You have heard about this. Some non-astrometric space telescopes provide now or will provide high accuracy images of the sky, and sometimes some sort of astrometric use of these images is planned, but not always is planned at all and not always optimal. So, for example, Euclid or Roman telescope. Should astrometric community take more care to make it possible to fully use this data? It is a tricky question also politically or socially and so on, funding and whatever. But a study is planned based on the legacy of Gaia experience and Gaia algorithms if we can process this data with professional astrometric algorithms and accuracy. Now, in the recent years, we have seen several unusual or unexpected applications of astrometry. Many non-trivial applications can be found in the papers of the community based on these 10,000 papers at least, based on Gaia data. I don't want even attempt to compile a list of those applications. Just one example. All of you, or almost all of you, have seen this fantastic picture of Ultima Thule from Deep Horizon. And without modern astrometry of stars, of Gaia, this picture would not be possible. Gaia astrometry was used to navigate this spacecraft to this object. Now, space source modeling from astrometric shifts between from high accuracy astrometry depending on the wavelengths. You have heard the presentation of Leonid Petrov, and this one example of this only. The famous radio optical offsets in the quasars. So something like 14% of ICRF3 sources have radio optical offsets. But much more will come when we have high accuracy infrared astrometry, also for stars, because this is really an information for source modeling. Then cosmology with astrometry of quasars, it is not quite unexpected, but it was not possible to do this before. Cosmic parallaxes or acceleration of the solar system, which was measured by Gaia. So this is from Gaia Data Release 3. Now, one more example, direct massive measurements of polarization, because the reflection depends on the polarization. You can do polarization measurements with Gaia data. And gravitational waves. Since I'm involved in gravitational waves, and this is unusual application, just 2 slides on that. So many people would be surprised, why, what is the problem? I mean, how it is related? Very easy. So all of you know that gravitational field produce light deflection. And gravitational wave, so this is the famous 1.7 arc seconds at the age of the sun, the famous Eddington experiment. But the gravitational waves is nothing else than a time-dependent gravitational field. And that is why this gravitational wave propagating through the solar system and through the position of the observer will cause time-dependent light deflection of all sources, coherent light deflection of all sources on the sky. The theory was developed already decades ago, and this is an example of such a signal. This is a global signal for a gravitational wave propagating in a particular direction toward the North Pole. And this can be used. So it is time dependent, and it can be used with Gaia astrometry, for example, which is also planned. Now, Gaia astrometry and actually all similar sort of astrometry can be used to detect very low frequency gravitational waves like here, but here we compete with pulsar timing arrays, but we also can detect higher frequency in this region between the application area of the pulsar timing and the future LISA mission. This is very exciting, actually, and if you check the literature, this subject is getting more and more appreciation and attention from the community. Now, this is my last slide, the conclusion, basically. So, at the moment, we have a very positive momentum in the development of astrometry. So the astrometry is really appreciated by the whole field of astronomy and astrophysics. And we can hope with all these projects and all these applications, and that in the decades to come, astrometry will continue to be an appreciated, highly appreciated tool for many fields in astrophysics. It should be multi-wave bands anyway, should be versatile, so different sort, global, small field, and so on. And astrometry is already now, so something like Gaia astrometry, the global astrometry, is already now a basis of many other projects. For example, Euclid would not work without Gaia astrometry, as it is planned right now, not at all. So, and also ELT and LSST will calibrate itself, and ELT, I mean, if you see on the sky something, you would like to know what it is and which coordinates you have. And Gaia astrometry with its density, and then later LSST astrometry will be crucial for that. Now, this momentum, current momentum of Gaia, of astrometry should be used, and it should be also supported by many new unconventional and unexpected applications, some of which I have tried to discuss with you. And there is one important and very important thing, young people in astrometry. Gaia is a great mission, but it has done one thing which is bad. It killed astrometry worldwide, the large community of astrometry, since Hipparchus started and Gaia continued this. Now Gaia has produced already a lot of results, and it is now time, with this momentum which we got from the community, to think very careful about inviting young people to astrometry and keeping those people interested. So I'm done. Thank you.
Thank you, Dr. Kleiner. We have time for one really quick question. Chris has a question.
Sergey, thanks for that great overview and placing Gaia's amazing accomplishments in context. Happy birthday to you and your whole crew. I think Gaia Data is going to keep people busy for probably another 2-3 decades. So again, please pass congratulations on to Gaia. I remember when you were just beginning and it was just a vision, and to see it realized is wonderful.
Yeah, thank you. Thank you, Chris.
Okay, in the interest of time, we'll move on. Up next, we have Christiana talking about VLBI astrometry and strong lensing to look at cosmology.
So thanks a lot, Lucas, and I would like very much to thank the organizers for giving me the opportunity to talk about maybe this unexpected application of astrometry, in particular VLBI. I would like to thank the collaborators who made the majority of the work I will be showing here today. So I hope to make this correct. Is this? No, let's try. This one. So before going into the details of the application, I just would like to mention what strong gravitational lensing is. So we have a distant background source, and for the purposes of these specific applications, it's a jetted AGN, whose light is deflected and magnified by the presence of a massive foreground object, which we call the lens. So because of the intrinsic nature, extended nature of the background source and the lucky alignment, we may observe these extended gravitational arcs. The position and the fluxes of these arcs, of the lensed images, are really important to determine the mass distribution of the lensing object. At the same time, these images are a magnified view of the very distant sources, which may not be able to detect currently with the telescopes today. So I will talk both about the lensing galaxy and the background source from an astrometric, a relative astrometry perspective. And so I will start by telling you how strong lensing and VLBI can really be powerful in inferring the mass of the dark matter particle. In particular, gravitational lensed arcs that are observed with VLBI because they can detect directly the subhalos that we expect to be very numerous from the cold dark matter model. So you see on the left a simplified version of the subhalo mass function, where the masses, where the subhalos with masses below 10 to the 7 solar masses are those that maximize the difference between a cold dark matter model and a warm dark matter model. The gravitational effect of these subhalos on the lensed images is of the order of a few milliarc seconds, as shown on the top x-axis. Or if you want, on the right, you can see a simulation from Giulia Despali, who will talk tomorrow about this together with John McKean. You can see that we can even detect directly the effect of these subhalos on the arc if we have enough angular resolution. And with VLBI, we can detect this milliarc second perturbation on these arcs. So that's why we investigated this issue with this arc, MGJ0751 plus 2716, which was observed with the global VLBI array. And we modeled this with a smooth mass density distribution, taking advantage of the high astrometric precision given by the VLBI observations. What we found on the right, you can see the mismatch that there is between the observed positions and the model predicted positions from a smooth mass density distribution, which is significant of the order of tens milliarc seconds, considering that the astrometric precision here is of the order of tens of microarc seconds. So another interesting part here is that this astrometric anomaly doesn't show a localized effect, but is generalized all over the lensed images, showing evidence more for a granularity effect, which has also been found in other systems. For instance, I would like to highlight this work from Hartley and collaborators 2019 on HS0810, where they also find this granularity effect on the same level, demonstrating that smooth mass density profiles do not work on milliarc second scales, or let's say at sub-kiloparsec scales. This is not surprising because we do not expect galaxies to be smooth at sub-kiloparsec scales. And so we may start to test and exploit the high astrometric precision given by VLBI to try to test more complex mass density profiles. And we can start by adding angular structure, and this is a work led by Powell 2022. Where we have a suite of complex models from left to the right of increasing complexity done in a Bayesian framework directly in the visibility plane. And when we include the angular structure, this is strongly preferred by the data. And this is also recently confirmed and from different works, also with ALMA, with the long baselines and HST. So this angular structure almost fits the data down to the noise level, but not quite, leaving us the room to test alternative dark matter particle models, which may perform better in fitting our radio arcs. And so we started from the fuzzy dark matter model, which is undistinguishable on large scales from the CDM, which is what we want. But on the small scales, on the galactic scales, actually it has this peculiarity of having the granules, as you can see from the scale here. And so maybe what we are looking at in JO751 is the effect of this granularity from the fuzzy dark matter. So we tested different dark matter particle models. Here, again, it's a work led by Devon Powell at MPA, published in 2023, from light particle models to heaviers, from left to the right, putting constraints on the dark matter mass that are as stringent as the Lyman alpha forest and the Milky Way satellites. Maybe this work demonstrates that if we have enough high astrometric precision from VLBI, even a single gravitational lensing system can be interesting or competitive for the dark matter particle studies. So I will now move to the source plane with maybe a more exotic kind of application for the search of dual AGN systems. And these systems are predicted to be an intermediate stage of the hierarchical structure formation scenario. And they are, however, very rare. This is shown on the plot on the right from the review of the Rosa and collaborators 2019. These systems are really rare in the local universe, but their fraction increases at high redshift. At the same time, the interesting systems to search are those that are close, so the tightest pairs, because they probe the latest stages of merging, which are the precursors of what the LISA interferometer will observe in terms of gravitational waves. So, of course, this poses the issue of having high angular resolution to spatially resolve these systems at high redshift. And in this plot, where we have a summary of all of the lenses of binary, dual, and offset AGN, we can see in green how the radio VLBI performs, even without gravitational lensing. So the bar indicates the redshift range covered by these searches, and you can immediately appreciate that only VLBI can go beyond redshift 0.5. Of course, if on top of that we can add the lensing magnification, we can even go at smallest separations. You see the green bars are indeed in the higher redshift range and in the smallest separation of the systems. So to date, we know only two strongly lensed dual AGN candidates. Sorry, I forgot candidates in the title, so they're not confirmed. One is PS J1721 on the left, which has been suggested to be a dual AGN candidate from radio and Gaia observations. While on the right, you have MG 2016, which is a very complex system, where the evidence for there being a dual AGN comes from VLBI, but multi-epoch VLBI observations, which enable the detection of very small proper motions in the source plane. At the same time, this provided us with a very precise lens model, which we use to reconstruct the X-ray emission. And this is a work from Schwarz 2021. You see the X-ray Chandra observations on the right, which adds more evidence for there being a dual AGN, because we reconstructed two X-ray sources, of course, with a bit larger astrometric uncertainty in this case. So the importance of this work is that if we confirm these two systems, then the detection rate might be an order of magnitude larger than what currently predicted by simulations. And so this kind of studies can be really interesting to test supermassive black hole formation and evolution models. However, we are really limited by the low number statistics here. And so we need many more strong lensing systems if we want to put stringent constraints on the dark matter particle nature, but also on the nature of the background sources, and test also the baryonic counterpart of our lambda CDM model. And so that's why we started to look for lenses in the wide field VLBI survey, so directly at millisecond scales. I just would like to mention that there is another work, complementary work from Casadillo and collaborators 2021 that used the AstroGeo database that has been presented by Petrov before, and that's very powerful to search for this kind of exotic systems. We used a different approach in the MGIV20 survey. I will not go into the details of the search, but we found two final lens candidates and two rediscoveries. We followed up these two lens candidates with a combination of the EVN and the E-Merlin. So we added intermediate baselines for this system, showing clearly that this is not a lensing system, but more FR2 galaxy. Even if this was a rejection of, and so we didn't find any new lensing system, it shows the importance of having sub-arrays in our future arrays in order to cover different angular scales and maybe directly finding, confirming or rejecting in one go this kind of systems. In the future, the SKA 1-mid surveys are predicted to find 10 to the 5 strong lensing systems. So this is especially because of the excellent sensitivity that you see on the right from the SKA 1-mid. However, the angular resolution will be enough to spatially resolve the lensed images. But if we want to pursue this kind of science cases, we will need the VLBI part, both on the SKA and the NGVLA in the northern hemisphere. And so only with the VLBI, we will be able to spatially resolve the lensed image structure, obtain high astrometric precision to constrain dark matter particle models and also the source science and understanding better the background sources. Moreover, we will be able to do this for the faintest systems. So this is a simulation from Lategan and McKean at the University of Pretoria for the NGVLA long. This system is like JO751, but 2 orders of magnitude fainter. And so this is the power of the future telescopes for this kind of science cases. So I will leave you here with my summary, and I thank you very much for your attention.
Any questions?
Christiana, considering that so great efforts were put for finding Banner agents and we still didn't find them, is it time came to revise theory and based on this huge false negative statistics, or it's too early?
Yes, that's a very interesting point. I think at the moment we have so few confirmation that I agree with you. We may need to better revise the models as we have. I'm not a theoretician. Clearly, I am an observational astronomer. But yes, that would be the time to do that.
Seeing none, let's thank our speaker again. Up next, we have, sorry, give me a second, Sergio Quiano, talking about dynamical masses of young stellar multiple systems.
Hi, can you hear me?
Sergio here. Oh, he's online. Online. Okay, thank you.
Yes, you can hear me, I assume. Okay, thank you very much for all of you to being present.
Oh, now we can hear you.
Okay. Thanks. Thank you very much for all for being here, and also to the organizers for accepting my contribution as a talk. Well, I'm going to speak more about VLBI astrometry. I will be focused more on the stars, and particularly more on multiple systems and the determination of dynamical mass of young stars. Yes, well, we have a lot of motivation to do these studies, because estimating dynamical masses is the most direct way to estimate the masses of stars. The stellar masses are very important for it's a very basic parameter of the stars that we would like to obtain, and this will will serve as a base for the validation of theoretical models of the evolutionary models. In fact, it has been previously with VLBA dynamical mass estimation. It has been suggested that the evolutionary models could underpredict the masses of low mass young stars. And having these estimated masses, we can understand better the stellar evolution, and in particularly also the evolution and the effects of binarity and multiple stellar systems. We use radio astronomy, where we have the nice thing that the angular resolution is limited by the longest baselines, and as we can put antennas across the globe, we can have angular resolution of images with angular resolution of the order of 1 milliarc seconds at 10 gigahertz, or even better at higher frequencies. So another nice things of doing astrometry of young stars with radio wavelength is that the observations are not affected by those, and the positional reference against quasars. These quasars are part of the International Celestial Reference Frame that we have heard about early. And then these distant quasars are gives a semi-absolute reference frame. So we are tracing this astrometry of these stars in this frame, and which is very good for astrometry. Radio stars produce non-thermal radio emission in their coronas, where the dynamical the activity of the coronas produce electrons, accelerate electrons to semi-relativistic velocities and produce this non-thermal radio emission with brightness temperatures above 10 to the 6 kelvins, and which are very good to observe and detect with the BLBI technique. We have mainly used these young stars to estimate the distances to young star-forming regions, nearby star-forming regions, and we have several works on this area, and that we have estimated very accurate the distance estimation, and then are now confirmed with the Gaia telescope. And these are very in very good agreement with Gaia, with the new Gaia results. So parentheses on my talk, I would like to say you that I have a poster that I will be presenting tomorrow. If you want to discuss more about stellar astrometry and radio wavelengths, I will be happy to meet you tomorrow on more about this and other subjects. So when in our works, in all BLBA observations, we have detected that many of these stars that we detect at radio wavelengths are not single stars, but actually form binary stars where we can detect both stars at radio wavelengths. The separation is around 10 milliarc seconds, and this won't be resolved by Gaia. And this is very important to keep also observing and doing astrometric works at stellar astrometric works using BLBA or BLBI technique. Because of that, we initiated this project called Dynamical Masses of Young Stars with the BLBA or Dynamo BLBA. It's a large program where we have more than around 300 hours, and we are studying 20 binaries and 1 triple systems, and that cover a large spectra of spectral types and also masses. And the ages of these stars are below 10 megayears. So these are very young stars. So the present work that I'm going to present now, has been done by my student, Yasmin Ordóñez Toro, who is a PhD student in Mexico, and she has led these results. The first result, very interesting result that she obtained is related to the Ophiuchus S1 star. That is the star that, I don't know if you see my cursor, but is this star in the middle of this bright nebula here. And it has been in the past proposed to be suggested to be a star in the class of B5 or B3, but actually no one has determined the spectra, has measured the spectra of this star. It has been suggested this because it has an associated H2 region and it's been illuminating all these stars. And the suggested mass for these stars, it's about 6 solar masses, and it's known to be a low mass companion. And in fact, in our VLBA observations, we detect both stars. The main stars is very bright, and we detect it in all the epochs, while the companion it's very weak, and we don't detect it in all the epochs, but in a few of them. And we can trace the motion of both stars in the sky, and could obtain the astrometry of both stars, and actually estimate the mass of each component. And here is the masses that we are obtaining. It's 4.1 solar masses for the main component and 0.8 for the companion. So we can see that the mass of the main star is much smaller than the 6 solar masses that it has been suggested. We did a little bit more investigation regarding this. We estimate the temperature, the effective temperature of this star, and also the luminosity, and we see that if we compare it with evolutionary models, it's in agreement with a star between 5 to 6 solar masses. And here is only one evolutionary model, but we did this for several. And the 4 solar masses is the gray square here in the plot to the right. Then the main conclusion of this work was that the evolutionary models, in the case of the mass of S1, overpredict the mass of these stars. So a second object that we are also studying now is this EC95, where we have a hierarchical triple system, where the components A and B, it's a tight binary, and that is being orbiting by a third component, the component C. And we did, this has been suggested to be as 4 solar masses star. And well, there has been some previous work on this. And in our work, we have many detection also for the components A and B, and only 4 detection for the component C. It's not very radioactive. The masses that we estimate for components A and B, that we can estimate it as a single binary. It's about each component is showing that is 2 solar masses per component. For the third component, what we did was something more peculiar. As we have determined the motion of the tight binary, we model the system as a wider binary, where the star here represent the mean position of the center of mass of the tight binary, and here the red and blue colors are the position of the companion. And we use orbitized software to see what is the most likely orbit of this star, and to estimate the total mass of the system. And we find that the total mass of the triple system is 4.8 solar masses, and then we can constrain the mass of the third component to be that is significantly lower than the components A and B, but below 1 solar mass, or around 1 solar mass. And these are the works that we are doing now, and we have 19 more objects to study. But most of them are lower mass stars. And we have to keep in mind that with the VLBA software, that DiffX software, we can study many more stars. For example, here I'm showing you the Orion case, where we are with one single observation, VLBA observation, we can recover and study hundreds of stars in the same observation, where a decade ago, this was not possible. We have to observe only one single star, and now we can observe 600. Well, this 600 radio sources that we see in the Orion Nebula cluster, and where we have detected 120 stars with non-thermal radio emission. And this is the future, and I will leave you now with the description of the BLB or dynamical mass of young stars with BLBA. Thank you very much.
Thank you, Sergio. Do we have any questions? Okay, I have a question. Have you given any thought or consideration to how SKA, VLBI, or NGVLA long baselines might increase the number of sources you can detect?
Well, no, I haven't given it at all. Of course, that will be a huge number because the sensitivity that you will start to have is much better. We have to see also that we have a similar angular resolution, a little bit not as good as the BLBA alone, but it will be of similar order. So yes, that is a very interesting question. I'm also positive that with the NGVLA, for example, we could study more wider system, but closer stars that are also not detected at optical wavelengths, but that we can trace the thermal emission. In the case of the NGVLA, we could trace the thermal emission of these stars, because in the very base of young stars, we have the base of the jets, and that could also be used for astrometric studies, and that will increase the number, because we will not only study non-thermal radio sources, but also thermal radio sources. That will be, I haven't given it I haven't seen it and do the calculation, but we will really have a nice number with that.
That's fantastic. Thank you. We have one more question.
Hi, thanks very much for this really interesting talk. I was just wondering, in your sample, like how embedded can you go for this method to still work? I mean, obviously some of the herbigs are quite isolated, but could you go down to more embedded sources? Is it possible? Or I don't know if you could just comment on that.
Yeah, we are not basically affected by those. For example, EC95, it has been estimated to be embedded with an extinction of around, it has been, it's depending on who do the estimation, it varies between 40 and 100 magnitudes of extinction. So we are not affected by extinction.
Okay, we can thank our speaker one more time.
Thanks.
Up next, we have Abigail Frost, and she'll be talking about optical and infrared interferometric astrometry.
Oh, sorry. Sorry. Okay. Oh, yeah. Cool. Right. Thank you very much to the organizers for giving me the opportunity to speak here today. My name is Abigail Frost. I'm an ESO staff astronomer. I observe the VLTI and work with a number of its instruments for my science. And I just wanted to kind of advertise gravity as an instrument for looking at also multiple systems, this time kind of on the main sequence. And because I'm before Sylvester's talk tomorrow, I may skip through a bit of introduction, just in case. Okay, so we know everyone uses interferometry. Interferometry is essentially combining different telescopes to simulate a much larger telescope. Because we are combining beams, we deal with an interference pattern rather than an image plane as we usually would. And a key component of the interferometer is the beam combiner, which does all the magic for us. Of course, this changes what we probe on the sky. We're no longer looking at image space in kind of XY space, but instead looking in UV space because the interference pattern of the telescope to the interferometer is essentially the Fourier transform of an image plane. And so, yes, when we are probing different points with our interferometer, they relate to the baseline, the distance between the two telescopes, and the wavelength of the observations that we're taking. And when it comes to optical interferometry, we have some key observables that we use. Unfortunately, optical interferometry is much worse affected by the atmosphere because of all the water in there than excuse me, than longer wavelength interferometry. And so we struggle to do the kind of imagery reconstruction for many, many different telescopes that we have with telescopes such as ALMA or VLA, for example. So we usually, as a first instance, tend to work with these observables instead. The first is the visibility. Essentially tells you about the amplitude of the waves that you're combining. And this tells you about the spatial extent of your source. Visibility is measured between 0 and 1. If your visibility is very close to 1, then your source is unresolved. If it's getting close to 0, then it's getting more and more resolved. So if you have a disk or an extended structure like that, then you will see it trailing off. And if you have binaries, for example, then you can often see a very nice sinusoidal feature as well. And the shape of that sinusoid and how regular it is will depend on the brightness of the two stars, for example. Another thing that we have is closure phase. We cannot retrieve the phase information directly in optical interferometry. And so instead, we look for a combined phase over different telescopes, which we call the closure phase. And this tells us about the symmetry of the source. So if your closure phase is exactly at 0, you have a perfectly symmetric source. If it's varying from 0, then you have something asymmetric. Okay, and now one thing that that is particularly cool about the gravity instrument, which was mentioned in the first talk of this afternoon session, is the fact that it has a spectrometer in it. So within your beam combiner, you also have a spectrometer element. And this allows us to not only gain those visibility and closure phases, but also to get some other differential qualities that we can measure as well. One key one, particularly that I use a lot with gravity data, is the differential phase. And so essentially, we're using an emission line within the spectra as a reference. We can gain information on spatial displacements between that line and the continuum. And so you can see an example of that from a paper on the right. This is looking at a YSO. And essentially, you can see how the region probed by the continuum is very small in the center here, but we can see how the bracket gamma line emission is varying around this central continuum. And I think this is attributed to a disk wind coming off of a protoplanetary disk. You can tell a number of different things from the differential phase. Different shapes tell you different things. You can tell you can learn about rotation. You can learn about expansion at the bottom from that W shape, and rotation from your S shape. And also because we have that high angular resolution, just from the long baselines that we use in interferometry, when you're modeling your observables, including the differential phase, you can actually attribute spectral features to specific geometrical components at this high resolution. So it's quite, and therefore to very accurate positions. So it can be very, very helpful. So here is a picture of the inside of the gravity instrument. We're definitely going to hear more from Sylvester tomorrow, so I'm not going to go into this in too much detail, but I just want to highlight that there are two kind of main ways that we can do astrometry with interferometry. So single beam astrometry is kind of something that all or almost all interferometers can essentially tell us. Essentially, this is what you get when you model your interferometric observables, that visibility, that closure phase, that differential phase potentially, and you're getting essentially the spatial positions of the stars in your systems. So, this isn't exclusive to gravity. You can also get this information from Pioneer and many other interferometers that exist. One thing that Sylvester will talk about tomorrow, I'm assuming, is a dual beam astrometry, where instead you have a very complicated metrology system within your instrument, highlighted by these purple boxes here. And you're observing in two fields simultaneously, and it's this laser metrology system which measures the evolution of the optical path difference within the interferometer, and that essentially allows you to get accurate position changes within the thanks to this metrology system. And Sylvester will talk about that tomorrow. What I'm going to focus on for the rest of this talk is single beam astrometry and how just kind of straightforward modeling of your interferometric observables can already tell you very accurate positions about your stuff in your systems. Okay, so I'm going to use two examples from my work to illustrate this. We've got two stellar systems here, which are both stellar multiple systems, which are both a bit strange. They've been looked at with spectroscopy extensively, and it was really interferometry, and particularly also the astrometry we got from interferometry, which really helped crack the case of these two systems. Now, these are massive stars, and just to give a tiny bit of context, I care about massive stars because they affect lots of different things. They are responsible, everything in purple and yellow here in this periodic table is related to the activity of massive stars. So they really affect a lot, including our own origins in the universe. They're also important for these gravitational waves we've been hearing out today. They were the first stars in reionizing the universe, and they have lots of their feedback and ionizing radiation cause a lot of feedback which can be felt on local and galactic scales as well. And binarity and multiplicity are very key for these systems. We think almost all of them exist in at least a binary system, and most of them are expected to interact as well. And this can irrevocably change the properties of these stars and therefore their influence and their fates. So going back to the examples, HC 138-937 is one of these massive binary systems. It's a weird one because it's magnetic. This is not common for O-type stars. And one thing that makes it even stranger is it has this beautiful nebulae surrounding the system. This is really quite a rarity for these massive stars. A magnetic field was detected towards the system of around 1,020 Gauss by Greg Wade in 2012. This nebulae is thought to be very young. A paper that came out this year by Lim thinks it's only 7,500 years old. Yes, it was determined to be a binary through an interferometric snapshot in 2014. And spectral data for the system look very, very strange. There's lots of lots of very complicated lines in the spectra, which are associated with its magnetism. And this makes determining what's going on in the system, particularly finding its orbit, and over time, it made it quite difficult because these lines were always confusing the analysis of the RVs and making things very difficult. So due to lack of data at periastron patches as well, meant that only 2 potential orbits could be found for the system. And it wasn't completely clear where this magnetism was coming from. And why do we care about this magnetism? Well, magnetism limits mass loss. And so that's obviously going to affect the final fate of the star and what's happening. So we wanted to work out what was going on here. And so we went to interferometry. And so here you can see an example of the gravity data. Here is our closure phases. Here's the differential phases. Here are the visibilities, and here's the normalized flux. We had data from 2 interferometers, Gravity and Pioneer. Gravity being operating in the K band at 2.2 micron, and Pioneer operating in the H band, a bit shorter wavelength, 1.6 micron. And so by fitting these observables, we used a least square minimization code called PMOIRED, which was developed by Antoine Moron, the VLTI scientist at ESA Garching. And essentially, we're creating a geometrical model to try and reproduce the emission we're seeing and reproduce these observables. The data here is in gray, and the model fit is in red. And so the final model is that binary. And we fit this to a binary model to 9 years worth of observations with this kind of high resolution, maximum resolution around 4 milliarcsecond. And within the different epochs, we can see the star moving. And so basically, we're getting very accurate positions for the system over that 9-year period. Here, you can just see the information across the orbit from the interferometric data. This is the combination of that Pioneer and Gravity data. We could already see in 2016, we could even see just between a couple of months, the movement of the system. And this astrometric information was really key in converging on a final orbit for the system, given all the complexities in the spectra that were causing everyone a lot of headaches. And so what we did was we combined this information with the spectroscopic data that existed. And in particular, we used this orbital solution binder developed by now postdoc Matthias Fabry, who was at Leuven when I did this work. And so we got all these accurate positions, but also a key thing about gravity is this spectrometer element that I mentioned. And this is very powerful because we can see we have this strong bracket gamma line in the emission of the system. And because we have that combined with very accurate millisecond spatial information, we're able to determine which star in the system held this emission. And I could only fit the data if this was only associated with the primary star in the system. I couldn't split it between the 2 stars. It had to be from the brighter star in the system. And that's interesting because strong bracket gamma emission can be an indicator of magnetospheric activity in confined winds. And that implied that the primary star was the only magnetic star in the system. And basically, those insights from the interferometry and most importantly, getting those accurate positions, getting that defined orbit, and getting a total mass for the system really launched a whole new investigation into the source. We went back to the individual properties of the stars. We did some spectral disentangling. We did some atmospheric modeling of those distant spectra to work out the properties of the star. And it appeared that not only was that bracket gamma holding magnetic star weird because it was magnetic, it was also different because it looks rejuvenated compared to its companion. That's weird. And essentially we thought, okay, what has happened to this star to make it change from its rather normal looking secondary companion? And basically using some hydrodynamical modeling, we showed that a merger seems to have created the properties of the current star. And none of that would have happened. We wouldn't even have looked into this if we hadn't have gotten that information and confirmed where the magnetic field was coming from, thanks to the infrared astrometry, pretty much. And if you want to look at the whole story, please check out the paper which came out earlier this year. And I want to give one last example before I finish. It's not just, a one system hack. This is another paper that I brought out a couple of years ago. So this was, again, it's a system where we had lots of spectroscopic data and we couldn't decide, well, the field couldn't decide what was actually happening. Two proposals have been made. So this is a system called HR6819. It got a lot of attention because it was claimed to have the closest black hole to Earth in 2020. But this was contested by a couple of people and they thought, I don't think looking at the spectra you need to have a black hole. Maybe it's just a post-interaction binary system with a faint kind of stripped companion. And so they were both looking at the same spectral data in that case, and it couldn't be decided using those data sets what was happening. So we turned to interferometry. In the first case, if the system was a triple, with a black hole at the center, which is what was proposed here, we would expect a bright source at 100 millisecond separation. We'd expect a BE star out here, and then we'd expect only one source in the center here. But if it was a binary, then both these stars would be in a close orbit. And so we needed to work out exactly the positions of these stars and work out exactly where they were. And that's where interferometry came in. So here you can see the similar observatories to what I showed you before. Here we have visibilities, here we have differential phases, and here we have a normalized flux. This is the UV plane, so this is just the points in UV space that the interferometer was probing when we took the observations. We had 2 epochs, which is why you can see some double points here. And again, we're seeing a very nice, beautiful double-peaked bracket line feature here in the gravity data, and you can see that feeding through into the differential phases as well. And essentially, when we fit this data, it was determined that we needed, it was a close binary. The 2 stars were only separated by around 1 millisecond, and this is below the resolution limit of gravity. But thanks to the this double peak bracket, oops, I need to go back. Thanks to this double peak bracket gamma line and the differential phases, we're able to probe that from kind of the emission of the disk. So we assume that one of these peaks is associated with the red shifted side of the disk, one of the peaks is associated with the blue shifted side. So even just from the flux in this case, we were able to tell something key about the system. And we fit that double peak feature with this disk model, and these disks are common for these BE stars, which we think were in these systems. And so it kind of fit the second scenario quite well, and we could rule out the black hole situation. And also ongoing work for this, a collaborator, Robert Clement, has been looking at the orbit of the system again. And you can see now we've done a lot of snapshots with gravity, and we're taking, and so we've got a lot more position information here. And this is important for us to look at in terms of looking at post-interaction systems, because we need to check, is this disk aligned with the orbit of the system? In this case, it is, which matches the ideas we have for mass transfer and things. But again, getting these positions is very important for ruling these things out and understanding these interacting binaries and these multiple systems in more detail. Okay, so that's me. Thank you for your attention. I hope I've convinced you that interferometry is a cool tool for looking at these systems. And check out Sylvester's talk tomorrow to hear about the exoplanet applications of the system as well. It's also not just stars and planets. We also have, the orbits of stars around the supermassive black hole at the center of the galaxy, which gravity is doing a huge amount of work towards. And so, yes, exciting things are happening with gravity, and check it out. I hope you are motivated to look into spectral interferometry after the talk. And thank you very much. I'll take some questions.
We have time for one question.
Cool, no worries.
A really interesting talk. I just don't know a whole lot about optical interferometry. So, okay. Next we have Fesasani van Ziel talking about multi-wavelength observations of AGN in the K-band reference frame.
Okay, so there we go. Okay. So hi everyone. My name is Fisi Fansel and I'm a postdoc at Hatario, and I'll be talking on behalf of a collaboration that we have going on that's working on using the connections from multi-wavelength correlations of astronomical and astrometric data of AGN sources in the Cape and Celestial Reference Frame catalog. Hope that made sense. So the Cape and AstroGeo VLBI project is a global VLBI project that measures AGN to improve and maintain the celestial reference frame. It was originally started in 2002. They had about 268 sources, which are shown in the image on the right. Since then, they've developed several programs which focus on astrometry, geodesy, imaging, and astronomy, among other things. And what we're particularly interested in is the astronomy VLBI program side of things. So this program uses VLBA observations at K-band, and they started regularly monitoring CRF sources in 2015. This program is mainly focused on sources at declination higher than -45 degrees. They run 24 sessions at 24 gigahertz once a month. And to date, they have high precision positions of 1,327 AGN and more than 5,000 high resolution images of these AGN. 731 of these are published in David et al. So the K-band project is mainly focused on CRF sources, which are mainly expected to be quasars and generally compact. But as we saw in Ms. Muya's talk earlier today, these AGN are not all perfect stable sources, which makes them ideal targets for variability studies. So why are we interested in this data? Well, we get images, and from these images, we can get fluxes. And from these images as well, we can get positions. So basically, we can study the time domain variability using data from a single project. We decided we wanted to leverage the extensive data from the VLBI observations to study temporal evolution of interesting objects. So we want to look at multi-wavelength cross correlations of the fluxes and also the positions. And we also want to look at imaging, focusing on the structural variability before, during, and after an interesting event like a fray. The potential of this program is that we can get to collaborate with astronomers in various fields, working on different frequencies, who will be also interested in the data we're working on. We can also trigger short-term or long-term observations depending on the activity of these sources. And it also helps improve our understanding of AGN behavior. But more importantly, it also improves both astrometric and geodetic models, making this a mutually beneficial relationship between the astronomers and the astrometry people. So can this data be useful for astronomical studies like time domain evolution? Well, we decided that we're going to look at this by using data from the VLBI. So we are using K-band data from the celestial reference frame from the monthly VLBA observation, sorry. And since we've got position, we also decided that we're going to take those, we're going to take that data as well.
which is at X band and K band. And we also recently also got data from IVS sessions at S and X band. So we've got position and we've got fluxes and we've got images. And we also decided that in order to study like a proper multi-wavelength evolution, we're going to look at gamma rays as well. So we're using data from the Fermi-Lat telescope, which monitors the gamma ray sky at 20 MeV up to 1 TeV and observes the sky every 3 hours. But because our VLBA observations are on a monthly cadence, we also decided that we're going to use the monthly light curves from the Fermi-Lat repository, light curve repository. So in addition to this, we also had the opportunity to get single dish observations from Hatarayo's 26-meter telescope at 22 gigahertz, which is K-band and X-band and C-band. And we've submitted a proposal which is looking at having regular observations, which are about 2 or 3 days cadence for these sources, so we can build long-term light curves for these sources in single dish. So how did we choose our sources? Well, we went to the K-band celestial reference frame and chose sources that were monitored VLBA regularly. And then from those sources, which were over 1,000, we chose sources that showed recent variability in gamma rays and in the radio as well. And we decided that we were also going to focus on sources that were at a declination less than 45, so we can study the southern sources. From these sources, we decided on 92 that we selected as our initial sample. And from these 92, 43 currently are being monitored at Hatarayo, but this may change depending on how good the data is. So the main idea was to look at sources that are mainly in the K-band celestial reference frame, and based on the results we get from the study, hopefully increase the cadence so that we can get more data so we can improve our results and build larger light curve repositories of these sources at different frequencies. So for today, I'm not going to show the entire 92 because we're still working on the sources, but we're going to look at 2 sources that we thought would be a good example to show. And these sources are 0234 plus 258 and 1424 minus 418. So the first one is 1424 minus 418. It's a well-known AGN. It's had long-term high cadence monitoring since 2012 at Hatarayo. And this source also had a neutrino detection in 2012, which was in the Nature paper written by Adler et al. And we also got to write an ATL on it, which is the Nemanashi Gilad and Oja 2013. So this source is highly variable in radio and gamma rays, but because it's too far south for the VLBA, the imaging isn't good. We can see we can see this from the light curves. Sorry. We took all the data that we've got in our repository. So the top data is the gamma ray data, which shows the flare that we had in 2012 and subsequent flares that have occurred since then. And currently it still looks like it's on a increasing trend. And then this is the data that we got from the VLBA. So you can see that it's still a bit scarce. It looks like it's also showing some variability, but we're not quite sure what's going on there. We looked at the position data, which looks to be relatively stable. I'm not sure, Namaka would have to tell me if this is what you guys expect. And then we also looked at the IVS session data, which is this light curve here that's also showing variability round about the same time with the first flare that we observed from the source. And we also looked at the single dish heart array data at 4.8 and 8.4 gigahertz. So as I mentioned, this source was clearly varying at all the scales that we were looking at. And although the VLBA data didn't look so good, we were still happy that we were getting variable light curves at the other frequencies. So when we ran correlations between the gamma ray and the single dish light curves, we noticed, okay, so then, so then after looking at the light curves and figuring out where the peaks are, we ran cross correlations using the DCF. And then we realized that from the light curves, we could get gamma ray and single dish correlations at about 100 days. And then we could also get gamma ray and IVS X and S band correlations, but we couldn't get anything with the VLBA since the data just wasn't enough to get a significant result from. Then we also looked at not PARCS, 0234 plus 258. And in comparison to the previous source, we could see that this source was also flaring in gamma rays, and we had a more significant peak with the VLBA data, and we think this is because the source is at plus 28, so it's towards the north. So the VLBA, I can see it better, so we can see the flaring peaks close to the gamma ray peaks more clearly. And that's the position data, but the SNX band IVS data for some reason couldn't give us any flaring activity like it did with the other source. So we're still trying to figure out what happened here. So we also got multiple variability from this source. The position looked relatively stable, and we had just started observing the source, so we couldn't get anything substantial in single dish. So for this source, we realized that we could get gamma ray and VLBA correlations because, of course, we can see that peak more clearly, but we couldn't get anything with the IVS and the gamma ray correlations because that data just didn't have any flares, and we couldn't get anything with the positions. And that's just the correlation plot at the bottom. I forgot to mention the correlation plot for the other one. But anyway, so we also decided that we're going to show some previous results from the astrometric positions correlated with gamma ray brightness. So Jeff Hodgson, who's one of our collaborators, decided to do a correlation from all the cross-correlation studies looking at the power law relationship of the Fermi gamma rays with the positional offsets. And he found that when he looked at all when he looked at all the repository data that we got from Fermilab and the positional data we got from the VLBA, 90% of the sources looked like they had a significant power law relationship, and most of them also showed a K-band correlation with S and X band correlations. There were no obvious trends between positive and negative correlations, and sometimes we would get different signs for different correlations, but this was just to see if the data was worth using. And the results from his correlations, the results from his correlations are on the right edge there. We try to do, this is for a specific source, 2131021, which we were using as an example to show what most of the light curves look like when we ran the power law relationships. And most of them show some peak in the correlations, but we're not sure if those are real or not. So we are currently looking at doing dedicated analysis for the Fermilab data, distinguishing where exactly the flares are, and then we'll try again to run the correlations and see if we see any differences. So key takeaways, what we were trying to do with this study is to figure out if we could use geodetic data for astronomy. So our results showed that this is possible because some of the light curves do show a peak in the K-band light curves, and we think that even with the sparse data, we could possibly sorry, I'm panicking. Okay, so even with the sparse data, examples show that some sources may have a positive correlation with the gamma ray data. And there are previous studies on gamma ray correlations with radio, but few include K-band VLBA data, which makes this a promising study and may help improve source structure modeling. We're hoping this project can isolate sources that may be affected by position accuracy, as Namakal mentioned before. And however, the interpretation on the physical mechanisms is still unclear, and possibly many mechanisms may be at play, but we still think it has interesting applications for geodesy and astronomy. So we've just started on this project, and we are still working on getting additional data. Recently, we got K-band, KVN plasma, Prahatra, Yabes, and Hobart, but we're not going to get any imaging from those. But we are also hoping to get K-band, EVN, and global VLBI data in the future, and more geodetic SX sessions for all the other sources. We're also still trying to run dedicated analysis on all the sources, like I mentioned, and we're also working on running significance tests for the correlations and investigating the connection with VLBA core flux density changes. Thank you.
Thank you for interesting talk. Why do you limit your study only to K-band?
Because we were looking at the celestial reference frame sources, and we wanted to focus on the K-band.
I would like to encourage you to look on the data archive. There's a lot of data also for Q-band, which are ongoing monitoring. U-band, we have tried to live in a huge universe. Observatory put a lot of efforts to make this data archive publicly available for you. It was not the case 20 years ago. Please use this treasure.
Okay, thank you.
It's not another question for you. It's just a comment. Thank you so much, Leonid. Yes, I think she just forgot. She actually did look at your database, and it is an absolute treasure. We're not just looking at K-band. That's where she started. There's also the SX data that she's looking at from IVS, and yeah, there's a lot of data available. So this is more just starting to look at how to use geodetic and astrometric data for these types of studies. But thank you. Yes, that will definitely also be included.
Let's thank our speaker one more time. And the final talk for the session is Dr. Ivanstov, looking at astrometric bias by inhomogeneous backgrounds.
Hello. Can you please allow me to share the screen? Yeah. Thank you. I would like to come immediately to introduction and say that there are a few basic, probably more questions that we met during making our measurements. First of all, they are all measurements are related to some background. Another point is that we can have different measures, how far our numbers are with respect to the background. And of course, the most interesting question usually we have is what is the boundary signal to noise ratio value for accepting or rejecting our measurements. While we can have different points of view on this point, I would like to give a view that there is a possibility to have some analytical results in this field. So I will first give a view about two-dimensional imaging when we have a Gaussian-like source and also some sort of background that we can present as some sort of radial symmetry background, and of course some constant. While we can keep the absolute value of the difference between the position of chosen pixel and the center of this background as big, we can get actually not a circle in the sense of background representation, but almost like a flat background. And of course, car will represent our gradient of background, and error 0 will be the center of our source of study. So actually, we can have a good insight if we choose some symmetry. There is such a cut if we take the center of the star, for example, and the center of the background, of the radial background. So in such case, the blue bell-like shape is our Gaussian, that is undistorted. The violet line will represent background, that is linear increasing. And the right curve will give a view of the sum of these two curves. So the usual case that we have in, for example, in imaging of stars, when, for example, the size of the star is quite small to the background variation. And in such case, yeah, the linear approximation is not so bad. While it is hardly noticeable that the red bell-shaped curve is shifted in the direction of the gradient. The right figure gives us the first derivatives, so you can easily see that the extrema, in this case maxima, the right maxima will be always shifted to the right side. Of course, there is a minima, and as far as it is not of our interest, I have not plotted it well. So we have succeeded in finding analytical solutions, so I would remain the formulas for the paper, and I will give a visual view of this function. So if we consider the photocenter bias ratio as a ratio of the shift with respect to the width of Gaussian, that we usually have a sigma, and the flux, the total flux that is given by the star as I0, then we can see that the shift, the actual shift of the sum of the, let me say, distorted Gaussian will reach sometimes 1. So it's not quite strange. Let me say that this effect is given by analytical solution. So you can see a smooth curve, while we would like to have these expressions in magnitudes. So in case we consider the difference of magnitudes with respect to background, and also we will consider the increase, for example, of gradient per the size of the Gaussian SK sigma as well in magnitudes, then our surface will have such, let me say, a smooth case. So perhaps the topographic map is much more clear when we can compare such analytical results with the measurements taken, for example, within a series of measurements, when we can calculate, when we remove bias in between these measurements, and we can calculate the standard deviation of each mean value. In such cases, for example, we will notice that if the increase of background is quite small, then we have almost undistorted Gaussian, and no shift is necessary. The right figure gives us the quantities in logarithmic scale, just as we would like to have usually for small quantities. So, for example, if we consider this sort of shift as an accidental error, for example, for the stars that are very close, for example, here is 0, very close to background, then we expect to have quite bigger dispersion of such measurements. And as soon as we are, for example, limited to the bright sources, the changes are quite small, and I think it's quite logical to have such results. And I will come to conclusions as the light background is present in each image, and today we can consider its inhomogeneity, and we can calculate the shift that will be produced to each source, image source. I didn't mention that the found solution actually can be applied to one-dimensional and two-dimensional images like spectra and usual imaging. With respect to the values, I have shown only the shift with respect to two-dimensional. However, for one-dimensional, I just omit, but there is a small difference with respect to that. As well, I would like to say that this background affects position of small signal-to-noise ratio objects, and it's quite clear there. It has a bound, upper bound, that is equal to the sigma, to the Gaussian needs. And there is a consequence that there is it's not a good idea to rely on the positions of objects with small signal-to-noise ratio. And usually it can be discovered while rejecting those faint objects from, for example, some sort of reduction in calibration. And as far as this faint object can be numerous, then the reduction and the solution will lose its good accuracy than it can have. So faint objects will always deteriorate the reductions in calibrations. And the weighted approach, of course, is necessary. The proposed linear model can be used in most cases. as I've told in the beginning, while the background gradient value within the image size is constant, and we can neglect of its change. And usually this is the case for astronomy, of stellar images. And as well, we have found the analytical explanation that can be applied to the discussion and description of the measurement errors while we plot them against magnitude. That's all. Thank you for your attention. I will be glad to answer the questions.
Do we have any questions? Okay. Chris has a question. Oh, announcements.
Hello. Tomorrow we're down the hall at 2.41 at 10:30 for the talks. The posters start at 10. I know we ran over during the coffee break. I think the posters are still up now for those that are still interested in that. So check out the posters. And we've set up a Zenodo site for people that want to deposit their slides or posters there and be able to see them. The IAU is going to give us 50 pages for 44 presenters for the proceedings. So I really encourage Zenodo so people can see more than, a page or so. So thank you. Thank you to all our speakers.